Yeah, hi, good evening, everyone. Am I audible? Hello. Okay, thanks, Varun. Okay, so today is the open session of Beak 7. So before starting the content of Beak 7, if anyone have any query, any question, AVL tree is not clear. Okay, so definitely today we will discuss AVL tree also. Okay, so this is the first topic of Beak 7. Just started watching Week 7. Okay, that's fine. So today we will just revise all the topics. So how we can solve the problems which is discussed in the Week 7. Also, we will discuss the main AVL tree. I know that that AVL tree topic is not easy. So we'll discuss that how we can solve on the paper pen first. After that, you will be able to understand the implementation. Okay, so only one answer. Any other? Anyone else? Okay. So let me share my screen and I'll start from the AVL tree first topic. Okay. So as you know that week 7 is started with the AVL tree. So what is the things we are learning for why we are learning this AVL tree? Because we have just finished one topic in the week 6 last that is called as a binary search tree. So if you know that binary search tree, what is binary search tree? So binary search tree is also a binary tree, but it contains a property with the value of the nodes. So some order is there. Okay, so what the property is? So every actually node in the binary search tree. So suppose if I'm creating three node in the, I hope my screen is visible to all.
Yes.
Okay. So suppose I'm taking some three node in the binary tree. So A, B, C. Okay, so there is some relation between these parent and child's node. Okay, so in child's we always said that this is a left child and this is the right child. Okay, so binary tree can contain only two child. One child is called left child and another is right child. Okay, so according to the binary search tree rule, all this left child value should always be less than to the parent node, and this right child value should always be greater than to the parent node. Okay, so this is the property in every part of the binary search tree. Okay, so if we just relate every parent node with the every parent node with the childs, okay, their childs, so this relation should be there. Okay, so each subtree of the binary search tree should contain this property. So if I'm just talking about some little more diagram of the binary search tree, so let's take one example. So like 5, 1, 8, 15, and 12 or 20. Okay, so here I have just created one binary search tree. So this property, you can see this property is fulfilled with every subtree as well as the complete tree. So if you relate this, suppose if we look this only one part. Okay, so if suppose if you look this only this part, so here this 1 is less than the 5 and this 8 is greater than the 5, right child. Okay, similar to this another part, here you can see that, so this 12 is smaller than 15 and 20 is greater than 15. So this property is similar. This 1, if it is coming on the left side of the main binary tree. Okay, so that means if we compare the root node with all the childs on the left side, so all childs should be lesser than to the main parent node where we are comparing. Okay, similar for the comparison of root node and all the child's nodes on the right side, so all the value of the right child's node should be greater than to the parent node. Okay, so we cannot create the diagram like this. If I just make another like 5, Okay, so 12 and 20, or let me just add one 9. Okay, so maybe there is a chance you feel that this is a binary search tree, because if you are comparing only this 9 with their parents, so this is coming on the left of this 12. Okay, so this is smaller than, so maybe this part you are feeling that this is fulfilling the property, but overall this is not fulfilling the property, because this 9 is comes on the right side of this root node. Okay, so but the value is 9 is smaller than this 10, so it cannot be come to the right side according to the binary search tree. So every nodes in the binary search tree which is coming on the right side should be greater than every node which is coming on the left side of any node, that should be smaller than in the binary search tree. Okay, so this is the property of the binary search tree. So if so, this is the first thing you have already learned in the week 6. So what is binary search tree? But what happened? So what are the advantage of the binary search tree? Can anyone tell me what is the advantage? Why we are learning this binary search tree? What are the benefits of this? Yeah, search in login times. Correct. Okay, so our main goal is here to perform some operations, so like searching operation, insert operation, remove operation in less time. Okay, so this is simply a data structure where we are storing some data. Sometimes maybe we will require that data, so we will search this data in our data structure, and sometimes maybe we have to add some new element in the data structure. Sometimes maybe we have to remove some data elements from our current data structure. So these are some common operations generally we perform with the data structures. So that operation how we can perform efficiently, so because of that we are creating this type of data structure where we can perform this searching, insert and delete operation in lesser time, not linear. We can perform this operation in login times. Okay, so how we can perform this login time? So suppose we have one binary search tree like this. So similar, this is the same binary search tree I'm creating again. So 10, 5, 15 and 1, 8, 12, okay, 20. Okay, so this is one binary search tree form where it contains total 7 elements. Okay, 1, 2, 3, 4, 5, 6, 7. Yeah, so it contains 7 elements, but the height of this is so if we consider the height of root node is 1, 2, and then 3. Okay, so total height is 3. So any element can be searched in this binary search tree in 3 steps. Okay, 3 comparison. If we start comparison from the root node, so we can easily find out. So suppose if we are searching 20, so we will simply compare with the root node. 20 is greater than 10. So we will ignore this complete left part and we will move to the right part. So after moving to the right part, we will move to the next element. Then we will compare again. So 20 is equal to 15. No. So 20 is greater than 15. So we will move to the right side. Okay, we'll ignore the left part. So now then we will move to reach at this 20. So after that, when we compare 20 is equal to 20, yes. So we found this element in 3 compare. Okay, similar to if we store 1024. Okay, so 1024 elements in this manner, so we can find out any element in 10 steps. So because if you find out the log n value for this uh 1024, you will get 10. Okay, so that means 10 steps, you in 10 comparison you can find out any element in 1024 elements. So this is very efficient operation. Similar, if you want to add new element, you can perform the same operation with log n time operation. So similarly, 10 steps maximum you can perform to insert new element in the current data structure. Same for the remove. So these type of common operation is beneficial if our binary search tree is balanced. So here I have created one balanced binary search tree. Okay, so binary search tree means balance means the height of the left part and height of the right part is approx equal. Okay, so here this is exact equal, but for algorithm purpose we are trying to create to make some approx equal. Okay, so there is no algorithm that create the approx equal height in the both side. Okay, but yeah, maybe one height difference is so this AVL algorithm is actually provide the binary search tree where the height difference is maximum 1. So we will learn how we so first thing is binary search tree. When if we create a binary search tree, so how we can get a unbalanced binary search tree. So suppose if we are inserting the elements in like this order, so 1 2 3 4 5 6, suppose elements are coming in this order to insert in the binary search tree. So first one element is comes into the binary search tree to insert. So initially empty binary search tree we have, so we will add simply binary one element. After that we want to insert this 2 in the current binary search tree, so we will always compare from the root. Okay, so you I hope you know that how we insert the element in binary search tree. So this is the also important operation you should know for the in terms of the quiz exams question. Okay, so you should know how we can create the binary search tree if any sequence is given. So here if we want to insert 2, so we will always start comparison from the root node, and we will check according to the comparison, if we will check where we will find out the empty place to insert. So here 2 we will compare from the root 1, 2 is greater than 1. Then we will move to the right, and right is there is no element, so that means this is the empty place to insert. So here we will insert 2 on the right side. Okay, so this become right child of 1. Similar for the 3. So always we will start comparison from the root. So just remember this, we will always start comparison from the root when we are inserting the element. So 3 is greater than 1. Yes. So we will move to the right. Right, there is one more element is there. So we cannot add here. So we will compare the element from the right element. So 2. Okay. So 3 is greater than 2. So now we will move to the right. Now there is no element on the right. That means empty place is there. Then we will insert here. So now this is the third element. Similar for the 4. 4 is greater than 1, greater than 2, greater than 3, then greater than after that we will insert is. Okay, on the right. So 5, similarly 5 will added here on the right. 6 will be added on the right. So same things, we are creating a binary search tree, but what we are getting some linear type of connections in the tree. Okay, so logically all are connected linearly. So this the height of this type of binary search tree is also equal to n. So suppose our elements are n, so here elements are total 6. Okay, we are just considering this n. So the height of this binary search tree is now equal to h equal to n. Okay, so now if you want to search any element in this type of binary search tree, so this will that searching operation will perform look like a simple list searching. Okay, simple linear operation. So you have to, suppose if you want to search this 6, you have to compare the 6 element. So all elements we are comparing here. Okay, so there is no benefits of this type of binary search tree where the height is not equivalent on the left or right side. So we cannot take the benefits of the efficiency if our binary search tree is not balanced. So because of that, when we are creating the binary search tree, we need to just balance the binary search tree. Okay, when we are creating the binary search tree, okay, at that time we will try to make balance. So that things actually this AVL tree is doing. So AVL tree is providing a balanced binary search tree. So some rule AVL tree have. So what is the AVL tree? Okay, so the purpose of AVL tree is to
Sir,
create a balanced binary search tree.
sir,
Yes.
sir, in
Yeah,
your
Harish.
case, if some elements are equal, then how
Hmm.
you will
No, in binary search tree we not store the equal element.
okay,
Okay, duplicate element we not stored.
okay.
So AVL tree. Okay, so what is the rule of AVL tree and what you should know before starting the AVL tree? So first thing is there is one rule, balance factor. Okay, so balance factor b suffix f, and the rule is left height. Okay, so this if we calculate the height. Okay, so left height minus right height. Okay, and the modulus value. If we calculate this value, okay, so if from for any node, okay, so if we are calculating this balance factor value for any node, so we will check what is the left height of that node and what is the right height of that node. So we will just subtract this left height minus right height, and we will check the modulus, this absolute value. So if this value is less than or equal to 1, so this is the okay condition. That means if we are getting this difference is less than equal to 1, so we will consider that our tree is balanced. So that means height of the left and height of the right part, okay, the difference is only either 1 or 0. Okay, that means both are same, or maybe one difference is there. Then we will consider this as a equal. If this condition is not true and we are getting more than 1, suppose we are getting the difference more than 1, 2, 3, 4 like this, so we will consider this as a unbalanced tree. Okay, if we are getting this difference is greater than 1, we will consider that our tree is not balanced. So we will apply some process to make balance. So what is the process? So first thing, this is the clear thing. Okay, so first thing you should know how we can calculate the balance factor. So I am just creating some diagram here for the example. Suppose this is a 10, this is 5, this is 15. Okay, suppose we have this binary search tree at some time. So here balance factor we always calculate for each node. Okay, so we will calculate the balance factor for this 15, for this 5, for 10. For each node we will calculate this balance factor. If we are getting this balance factor value greater than 1, then we will apply some process to make balance. So let me just calculate this balance factor for 15. Okay, so 15 balance factor, so that means we will calculate this height like as a, we will just consider the longest path on the left side from this current node to any leaf node, longest path. Okay, we will consider that number of edge or number of nodes in between, how many number of nodes are coming in that path, or maybe how many edge are coming in that path. So we can follow any fixed rule. So you can just calculate the number of edge. If you are counting the number of edge, just count the number of edge in the whole diagram to calculate the balance factor. Okay, if you are counting the number of vertex in the path, so just follow the same rule for the whole tree. So suppose if we are just considering that the number of edge in the path, so there is no left part, so that means 0, there is no edge is connected in this side. So 0 height we will consider on the left, and 0 height we will consider on the right. So here difference is 0 minus 0. Okay, and we are getting 0, so we will just mark here 0 balance factor for 15. Similar for the 5. So 5, 0 height is on the left, 0 height on the right. Okay, so 0 minus 0, we are getting 0 balance factor here. And for 10, so if you consider the number of edge in the longest path, so one edge is there only, and similar to, there is only one path from 10 to 15, so one edge is there, so 1 minus 1, so 1 minus 1, you are getting 0, so 0 balance factor for 10. Okay, and what is that this longest path means? I am taking another example to make more clear. Like 12, 20. Okay, so this is the another possibility of this binary search tree. So this is also a binary search tree. Now we want to calculate the balance factor for each node. So here always leaf node, the balance factor difference will this height difference will always come 0. Okay, so you can just consider as a base case thing. So there is no left, no right, 0 minus 0, 0. Okay, so you can just mark on the leaf node balance factor value is 0. But after that, suppose if you want to calculate this 12, what is the balance factor for this 12 node? So here there is only one path from 12 to 11 on the left side. Okay, so one edge is there. So we will consider as a 1 height, and right height there is no right part, so 0. So 1 minus 0. Okay, we are getting 1. So we will consider as a 1 balance factor here. Now if you want to calculate the balance factor for 15, so you can see that on the left side there is a longest path from this 15 to 11. So this is the longest path. So how many edges are coming in this side? 2. Okay, and on the right side there is only one path. So 15 to 20, there is one edge. So what is the difference between? Is 1. So balance factor difference is balance factor value is 1 for 15. Now what is the balance factor for 10? So what is the longest path on the left side? So only one path, 10 to 5. So 10 to 5, one edge. So left height is 1. And what is the right height now? So you can see that there is two paths possible in the right side. So there is one path, 10, 15, and 12 and 11. Okay, so this is the one path, and another path is 10, 15, and 20. So which one is the longer? So you can see this one is the longer path. And how many edges are coming in this path? 3. So we will consider this as a right height, longest one. Okay, not the this second one. So that means the right height is 3. So we will consider this as a right height. So 1 minus 3, we are getting, what is the absolute value? We are getting 2. So now the balance factor value of 10 is 2. Okay, so now you can calculate the balance factor in that manner, first thing. So this should be clear for everyone when you are just solving any AVL tree. So how we can calculate the balance factor for each node? So you can see here all nodes have 0 and 1 only if we expect this 10. Okay, so this is the main one node which contains the more than one value. So that means our binary search tree is not balanced. We are getting more than one balance factor on any node. So this binary search tree will be considered as unbalanced, and we will apply some process to make this as a balance. Okay, I hope this part is clear. How we can calculate the balance factor, first thing.
So you have to select the longest node, like longest
path.
route. Yeah.
Longest path from root to leaf.
And sir, so we count the number of edges and not the nodes in the longest path.
You can count anything. So suppose if you are counting the vertex, so follow the vertex rule in the whole things. Okay, so you will get the same difference. Suppose if you are counting always the number of vertex in the path, so here you will get 2 left height, okay, 2, and on the right side you will get 4. So similar things, you will get the difference only always 2.
Okay, yes sir.
Okay, so you can follow any one rule. You can count either edge, or you can count either vertex in the path. Okay, so you will get the similar balance factor. Yes.
So how are you calculating it too?
This difference, we are calculating the absolute value. 2 minus 4. Yes.
You just said that you are calculating edges, right?
So because of someone is asked, can we calculate? Can we count the number of vertex in path? So if we count the number of vertex, so this 10 to 5. So there is 2 vertex, 10 and 5. Okay, 2.
Yeah.
And in this part 10, 15, 12, 11. So there are total 4 vertex. Okay, and still we are getting the same balance factor difference. Okay. So here you can follow any one specific rule. You can go with this number of edge in the path, or maybe number of vertex in the path when you're calculating this balance factor. Okay, so this should be clear first things when you are just learning this AVL tree. If this part is not clear, you cannot go ahead in the next level of this. So I hope this is clear. Next part is the process to make balance. So here we apply the rotations on the binary search tree. So rotations, so what type of rotations we apply? So there are some conditions and there are some type of rotations. So we will see the condition and what type of rotation we will apply on the tree. So first, so I'm just mentioning some name. Okay, so first is left rotation. Okay, second left right, third right, and 4 right left. Okay, so this left rotation, so these are some these are 4 rotation. You should know how we can apply this 4 rotation and what is the condition when we should apply this rotations. Okay, so left rotation, left right, and right left. Okay, so first we will check. So this L, L, and R are just similar, but on the reverse binary search tree. Okay, and similar to this L and LR and RL. So first we will check this LL and RR condition. So what is the rotation of this first rotation LL, and what is the condition of to apply this? So suppose if we are inserting some binary search tree, so and our sequences look like this. So 10 element is coming first, after that we are getting 5, and after that we are getting 1. Okay, so suppose this sequence is coming to insert. So 10 will be insert first. Okay, and this process, so when we insert the element, we will always insert by the binary search insertion rule. Okay, so similar, we will always add the node in the same way which we are adding in the binary search tree. But after the insertion, we will calculate the balance factor for each node. Okay, and then we will check if we are getting more than one balance factor for any node, we will apply rotation. Okay, so this is the process we will always apply after the insertion. We will check the balance factor for each node, and if required, we will apply the rotation. So if we have added this 10 in the empty binary search tree, so we are getting only one node. So here, what is the balance factor for this is 0 left hand, 0 right hand. So 0 minus 0, 0. So there is no need to apply some rotations here. But now we will insert the next node. So this is 5. Okay, so previous, always we will insert in the previous balance tree. So this is already balanced, so no need to do anything. So we will insert 5 in this. So 10 and 5. Okay, so 5 will insert on the left because 5 is smaller than 10. Then move to the left part, and the left part is empty. Then we will add here. So after inserting here, we will calculate the balance factor for each node. So leaf node balance factor is 0 minus 0. Okay, so 0. And when we calculate the balance factor for 10, so what is the left height is 1. Okay, 1 edge in the longest path. And what is the right height is 0. So 1 minus 0, 1. Still, you can see that we are getting 0 and 1. So this is okay. So we will consider this as a balance. Now we will add next element 1. So in the previous binary search tree, we will add. So this is the previous one, and after that we will check 1. So 1 is smaller than 10. Yes. So we will move to the left. It's smaller than 5. Then move to the left and empty place. Okay. So here we will add. Now this is added. Once again, we will calculate this balance factor for this node. So balance factor for leaf is 0. Now for 5, so what is the left height of this 5? 1, and right height is 0. Okay, so 1 minus 0, 1. Correct. And balance factor for 10. So you can see that what is the longest path? What is the number of edge in the longest path on the left? So 2, and right is 0. So 2 minus 0, 2. So here you can see that you are getting this balance factor 2 in the binary search tree. So if you're getting this type of situation, now which node you are getting this balance factor more than 1 from the bottom side? Okay, so there is a chance when you are adding this type of binary, if you are adding some nodes in the binary search tree, so maybe you will get this balance factor more than 1 on maybe 2 or 3 nodes at the same times. So you will always solve the node which is coming first from the bottom side. Okay, so this is not in the case for the current. We will just give some example for that case also. Okay, so here we are getting the balance factor more than 1 on 10. Okay, now from this 10, we will check which side the height is more. Which side height is greater? Left side. Okay, so we will just consider that left side from the 10. Okay, now we will move to the left child of this. Now we will move to the left child of this. Now once again we will see from the left child. Okay, which side height is more from the 5?
Left.
Okay, so if you are getting this type of situation, so this is the L and this is the L, so you are getting this LL. That means height is greater on the left and left side of that. Okay, so always just check, start from this 10 vertex where you are getting this more than 1 balance factor. Okay, check from there which side height is greater. Okay, left side. Just move to the left child and once again check which side height is greater. So left side, that means you are continuously getting LL. Okay, so that means this is the case LL rotations. So in this case, if you are getting this type of situation, so what type of rotations you have to apply? So here, this is the pivot position you have to just take. So just consider this 10 position as a pivot element and shift this 5 at this 10 place and shift this 10 onto the right. So you can see that if you consider this as a pivot point and just rotate this as a clockwise. Okay, so the positions are fixed, only you have to rotate in the clockwise direction. So just shift this 5 at the 10 place. Okay, so this 5 will come at the 10 place, this 10 will move to the lower right, okay, this side, and 10, and this will become 1, this clockwise direction. Okay, so you have to just remember this rotations when you are solving this on the logically on the pen and paper. So this is the clockwise direction you have to rotate. You are, if you are getting this LL type of rotations, and a rotation you have to apply on the node where you are getting this more than one balance factor. Okay, so just make this as a pivot and just pull this 10 onto the right side. So you will get this rotation like balance tree. 5 is coming on the top, now 10 is shifted to the right, and this 1 will be shifted on the 1 position up. So now you can see that after applying the rotation, if you calculate the balance factor, you are getting 0 balance factor for 1 and 0 for 10. Huh.
Sir, we have to take a pivot as 5 or 10.
Of 10. In this case, 10. Okay.
Can you just once again repeat this? I just missed it.
So okay, here in this case, LL type of case, we consider the position of the node where we are getting the balance factor more than 1 as a pivot position, and we just pull this onto the right side from this position. So this 5 will come at this 10 place, and 10 will be shifted to the right down place. So you have to rotate this this part, okay, into the clockwise direction. Okay, just move this 5 on the this 10 place. Okay, so location of this 10 is now replaced by the 5, and this 10 is shifted to the right.
But
Okay,
it
now
appears that 5 is functioning like a pivot, no?
no, why 5 is
Because it is going and sitting as a root node.
no. So actually you are just confusing that. Suppose some part is connected with the above things. Okay, so suppose some remaining balance such T is connected on the above. Suppose I am just making some diagrams. Okay, A, B, C. Okay, and this part is coming here, like, okay, so 10 and 5 and 1. Okay, now suppose we are working on here. Just consider that this part is already balanced and we are just rotating this. Okay, I'm just taking some example. We cannot consider this 5 as a part because after rotating, so okay, so this is connected with the parent node. Okay, 10 is connected with the parent node someplace. So when we rotate this, okay, so we cannot do like this. So 10, okay, so this connection will be removed from the B. We are not doing this. What we are doing, we are simply shifting. What we are doing, we are simply shifting this 5 at this place. Okay, so this will become 5. Okay, so this will connect it with the parent. Okay, where the 10 is connected in the previous. Okay, and now we will create some new node where with this 10 will be shifted, and now 1 will come here, and this will be removed like this. Okay, this. So this connection is happening in that way. So on the 10th position where the 10th node was there, at that we are considering as a pivot. So we are shifting, we are rotating in that manner. Okay, so position of the 10, we will move this 5 at the position of 10, and we will just move to the 10 onto the right side. So this connection should not be break, which is already connected in the before. So there is a chance. Okay, so pivot is 10 here. So this is simply like this. So you are pulling this 5 on this position on to the right. So all nodes which are coming on the right side move to the one position above, and this 5 will come at this position, this one will come at this position, and this will shift it to this position onto the right. Okay, so after that you will get this part after a rotation of the clockwise direction. After that you can calculate this balance factor for each node. So you will get, you can see that the balance factor problem is now resolved.
Sir,
Yeah, 0.
like if we have so many like left trays 4 to 5 times bigger, then we start with the root node or rotation or from the last node.
No, actually what happened, we always check this process after one element insertion. Okay, we will not apply this ABL tree logic on the random tree. Okay, when we add one new node in the binary search tree, we check this what balance factor we are getting. If any balance factor is greater than 1, we apply this process. So you will not get this type of situation where the all nodes on the left side, like 4 nodes are coming on the left side and no node is coming on the right side.
Yes, okay.
Okay, so this type of situation will not come because we are always checking this process after only one element insertion. So you will always get maybe 2 balance factor or 3 balance factor on any node. So this is the maximum things.
Okay, sir.
Okay, so I'm just explaining now rotation type. Okay, after that we will take some example and to explain. Okay, so what type of things we will get. So this is the LL condition. The reverse condition, just reverse condition of this LL. So this the second is RR. Okay, so suppose if we are getting sequence like this 1, 5 and 10. Okay, for insertion. So here we are inserting this one first, balance factor is 0. Okay, so after every insertion we will check this. Okay, so after that no problem with this binary search tree. Okay, balance factor is 0. After that we will insert 5. So 1, this is the previous binary search tree, and now we will insert 5. So 5 is greater than, so this will be added on the right side. Now balance factor of 5 is 0 and balance factor of 1. So left hand is 0, right hand is 1. Okay, so 0 minus 1, 1. So this is 1. Okay, still no problem. Now we will add one more. So 1, 5, this is the previous, and we will add 10. So 10 will insert here. Okay, so 10 is greater than 1, greater than 5, then we will add here. So now balance factor of 10 is 0. Balance factor for 5 is 1. Okay, so 0 left hand and right hand is 1. So 0 minus 1 is absolute value 1. And for this 1, okay, so left hand is 0, right hand is 2. So 0 minus 2, 2. You are getting 2. Now you can see balance factor you are getting 2. So same things we will check from the node where we are getting more greater balance factor. So which side the height is greater from this node? Right side. Okay, just move to the right child of this node. So 5, and check again which side height is greater. Right side again. Okay, so continuously you are getting right and right. So this is the RR type condition, and we will just apply the reverse rotations which we have already checked in the previous. So here we will consider that as this is a pivot position. Okay, 1, and we will just pull this onto the anti-clockwise way. Okay, so we will just pull this on the left side from this one part. Okay, just think about that. This is all these nodes are connected by some thread, and you are pulling this one node by this pivot position. So this 5 will be moved to this pivot position, and 1 will become at the left part. Okay, so after applying this anti-clockwise rotation, you will get this 5 and this 1 on this side and 10 on the shifted to the 1 upper. Okay, so this is the rotation anti-clockwise. Okay, after that you are getting 0 balance factor for this, 0 for this, and 1 minus 1, 0 for this. Okay, now you can see that this balance factor problem is now resolved after rotation. Okay, so this is RR rotation. So you have to just practice some example, but you should know what is this LL rotation, what is this RR rotation. So there are 4 type of rotation. After understanding these rotations, just take some examples and solve these problems by applying this. Okay, so and third one. Okay, now LR. So this is the next case. Suppose if we are getting a situation like 1, not this 10, and after that we are getting 5, and then we are getting 8. Okay, suppose we have say this type of sequence. So okay, this 10 will be insert here, 0 balance factor, no problem. Now we will add this 5, so 5 will be added here on the left side. Okay, so 0 for 5 and 1 for 10 balance factor. Okay, so still no problem. Okay, then we will check for 8. So 10 and 5 is there. Now 8 we will check from the root. 8 is smaller than 10, move to the left. Now 8 is greater than 5. Okay, so greater means this should be come onto the right. Correct. So we are simply adding by the insertion process of binary search tree. So after that you can see that balance factor for 8 is 0, balance factor for 5 is 1, 0 minus 1. Okay, balance factor for 10. So balance factor for 10 is 2 on the left or 0 on the right. So 2 minus 0, 2. Okay, so now this is a not balanced. So in this case, just check which side height is greater of the 10. Which side?
Left.
Left side.
Left side.
Okay, so left side. Okay, now just move to the left child and check which side height is greater from the left child. This 5.
Right side.
Right. Okay, so this is L and R. Okay, so this is the type of LR condition. In this case, we applied 2 rotations. First rotation we will apply on the node which is the child of the node which have the greater balance factor. Okay, so this is the violation on the node where we are getting more than 1 balance factor, and we will check what is the left child of this. So this is the 5. So first rotation we will apply on the child node. We will consider this position as a pivot position, and we will apply the anti-clockwise rotation on this 5. Only this part. Okay, this part we will apply this anti-clockwise rotation. So after 1 rotation, so we will get this type of binary search tree. Okay, so this 8 will be shifted to the 5 position, and this 5 will be shifted to the left. Okay, so this is the first rotation we applied on the 5, and second rotation we will apply the node where we are getting this balance factor more greater than 1. Okay, so this node, and here we will apply the clockwise rotation. Okay, now this 8 will be shifted at the 10th position, so 8 will come at here, and this 10 will be shifted to right, and this 5 will be shifted to here. Okay, so now you can see that after applying the rotation, so one important thing is when you are applying the rotations, you should get the balanced binary search tree. Okay, so binary search tree property should not be violated. Okay, so here after rotation, you can see this binary search tree property is now fulfilled. Still okay, this is not violating. So 5 is smaller than 8, 10 is greater than 8. Okay, so now you can see that after rotations you are getting this is as a final binary search tree after 2 rotations. Okay, so this is the first rotation, and after that second rotations. First, and this is second. Okay, so now balance factor for 5 is 0, 10 is 0, 8 is 0. Now all balance factor are now reduced and coming in the basic condition, less than equal to 1. Okay, so this is now balanced binary search tree. So this is LR situation, and fourth one is RL. Just
So could you
reverse of
repeat that LR in first rotation we focus only on the 5 and 8.
not we will always apply the rotation on the child. Okay, which side we are getting the higher height, we will just consider what is the left child of this 10. So this is the left child 5. We will consider this position as a pivot position, and we will apply the rotation only the lower part of this 5. Okay, so simply we will rotate this as a anti-clockwise this part. So this 8 will be shifted at the 5 position, and now 5 is shifted to the left here. So this part is now rotated in the first rotation. Okay, after that second rotation we will apply on the main node where we are getting the balance factor greater than 1. So this is this we will consider as a pivot position now, and now we will apply the clockwise rotation. So clockwise, after shifting this, so this 8 will be shifted to the 10th position, okay, here, and now this 10 will be shifted to the one down, okay, on to the right. So you will get this as a final. So
Okay, sir. Yeah.
okay, so this is the two rotation we have to apply when we are getting this LR type of situation. Okay, similar is RL, just the reverse things. Okay, so if we are getting like sequence 1, then 7, then like 5. Okay, so 1 we will insert here. Now balance factor is 0, and when we insert the 7, so 7 will be add on the right. Okay, so 0 balance factor for 7 and 1 for 1. Okay, when we insert 5, so 1 and 7, so 5 is greater than 1. Okay, move to the right. 5 is smaller than 7, so this will come on this side. Okay, correct. So after that we will calculate this balance factor for 5, 0, this is 1, and this is 2. You can see that right height is greater than, so right height is 2 and left height is 0. So this difference is 2. So this is unbalanced now. Okay, so same things we will apply in the reverse way now. See, we will just find out the what is the child of this 2 on the right side now. So this is the 7. Okay, first rotation we will apply on the 7, this node, and this rotation will be happen on the clockwise direction. Okay, so this part only we will rotate. Okay, so this is the first rotation. So after that you will get this change. So 5 will come at this 7 position and 7 will be shifted to the right. Okay, after that second rotation you will apply and consider as a pivot element, this one node. So this is the anti-clockwise rotation. So 5 will be shifted at one position. So 5 and 1 will be moved here, and 7 will move here. Okay, so you are getting the final balance tree here. So this balance height is 0 and 0 and 0. Okay, that means this 2, this is the greater than 1. So this condition is now resolved after 2 rotations in this case. So this is the balance part. Okay, so these 4 are the main rotations for the AVL tree, you should know. I hope this is clear.
Sir,
Yes.
sir, when to decide left or right rotation? How to decide this?
Left and right,
Yes.
based on this condition, what condition we are getting. So in this case, what type of condition you are getting. So just check from the node where you are getting greater than 1 balance factor. So 2. So just consider this node and check which side height is greater. Right side.
Yes.
Okay, and just
Yes.
move to the right child. Okay, and check that which side height is greater. Left side.
Yes.
Okay, so this is the RL case. So in RL case, we always apply the rotation on the child first in the clockwise direction. Okay, so first we will apply the first rotation on the child node, and this is clockwise rotation, and second rotation we will apply on the main node where we are getting more than 1. Okay, so this is the anti-clockwise. This is the second rotations. Okay, so this is the fixed rule. First initial things you have to learn this type of rotations. Only these are 4 rotations. Okay, just learn that what are the condition, how we will identify the condition. First this RL and LR, this type of condition, and after that which rotation we need to apply. Okay,
Okay.
so and these are the main 4 rotations, and some condition actually comes in between when we apply this rotation. So some condition comes. Actually, I am just explaining that what type of condition comes and how we handle that. So first thing is I've already explained these things, I think. So if we have like binary search tree, okay, after adding, so like this. Okay, so suppose we are adding this last node as a this node is the last inserted node. After that we are getting the unbalanced binary search tree. Okay, so there is a chance when you are calculating the balance factor, so maybe you are getting 2 balance factor here, 2 here. Okay, so maybe 1 remaining part is 0. So this type of situation may occur. So when you're calculating the balance factor after insertion, so maybe you are getting 2 balance factor here, 2 balance factor here, or maybe or 3 here, 3 in the above part like this. Okay, so which part you have to consider first to rotate? Okay, so from the bottom side, which node is coming which have higher balance factor? So you can see that this node is coming as a highest balance factor before the above one. So you will apply the rotation by considering this node as a unbalanced. Okay, only this part you have to apply the rotation by the rules. Okay, so once you apply the this rotations rules on this part, automatically this will also resolve. Okay, so if you make this part as a balance, so the this above balance factor will also reduce after rotations. Okay, so always apply the rotations from the bottom side which are coming first, which is where the balance factor is greater than 1.
You said the highest difference, sir.
No,
Three
2
is the highest.
maximum. Yeah, I think 3. Most of the time you will get only 3.
No. You said you should choose the highest difference.
Not highest, not highest. I am saying that balance factor which is greater than 1. Okay, so
Greater
here
than-
suppose, yeah, here you are getting 2, here you are getting 3. So which node contains the balance factor greater than 1? So there are 2 nodes. Suppose this is A, this is B. Okay.
So 3 also greater than 1. Why are we
Yes.
not choosing that?
So because of that, I am saying if you process only the lower part, if you make this part as a balance, automatically this will also resolve. This balance factor also reduce after rotations.
So the rule is to choose the lowest part.
Yes, lowest one from the bottom. Okay, so always apply the rotations on the node which are coming first from the bottom side. Okay.
Greater than 1 and from bottom side.
Yes. Okay, no need to apply the rotations on each node, because when you solve this part and when you just make balance this part, automatically the above one balance factor will reduce. Okay, so only one rotation you have to apply. So this is the one condition you have to remember during this process. Another situation we have, one more situation we have. So like suppose I am just creating one example here. So 10, 5 and 15. So 3. So this is still balance. Okay. So 8. Okay, so now it's still balance. Okay, and if we add 7 here. Okay, so I'm taking some example. Let me suppose we have inserted some nodes and we are getting this. Okay, and we are getting this one. So still this is a balanced. Okay, so how this is balanced? If you calculate the balance factor, so this is the 0 and this is still 0. So here 1 minus 1, this is also 0, this is also 0. Okay, and what is the left height of this 10 is 2 and right height is 1. Okay, so 2 minus 1 is 1. So this is a balanced. Okay, so after suppose we add one more element in this 7. So where so this 7 will be added. Okay, so if we add this 7, we will get this type of binary search tree. So 5 and 15 and 3 and 8. Okay, so 7. So this 7 will be added. So 7 is smaller than 10. Okay, move to the left. Greater than 5, move to the right. Smaller than 8. Okay, 7 will add here. Correct. So here this is the one case. Okay, so this. Okay, fine. Okay, let me take one simple first. I'm adding 9. So I'm adding 9 here. So 9 will be added here. Okay. So if you calculate the balance factor for each node, so 0 for this, 0 for this, leaf node, all 0. Okay. So when we calculate the 8, so balance factor on the left, height on the left is 0, right is 1. So 0 minus 1, 1. Okay. And balance factor difference from for the 5. Okay. So left height is 1, right height is 2. So 1 minus 2, 1. Okay. For 10, What is the left height?
3.
3. Okay, what is the right height? 1. So 3 minus 1 is 2. So you can see that here you are getting 2 balance factor on 10.
Sir, for 10, the left height is 2, right? 2 edges are there.
Longest path. Just look the longest path.
Okay, yeah, correct.
Okay, longest path 10 to 9. Okay, this is the longest one. And here we have 3h. So we are getting 2 balance factor on 10. And what type of situation is this? So from bottom, this 10 we are getting where the balance is not correct. The balance factor is not correct. So what type of situation is this?
Greater than one situation.
Hmm?
Greater than one situation. No?
No, I'm asking the rotation type. This is LL, this is RR, this is LR, this is RL.
LR rotation.
Yeah, so just check from the 10 which side height is greater. Left side. Okay, so this is left first. Okay, and comes to the child node 5 and check which side height is greater. So right. Okay, so this is LR type. Okay, so first things we will apply first rotation on the 5 and this rotation is anti-clockwise. Okay, so we will rotate this first. So here we will get this 10 and after rotation this 8 will come at the 5 place and 5 will move here and 3 will move one position down and this 9 will be shifted one position up. Okay, and this 15 is now will remain same. Wait one second.
Sir, can't get this. Can you explain this again?
Okay. So this is the LR type. Okay, so this L and R. Okay, so from the 10 node, left side height is greater. Okay, so this is the first L is coming, and after moving to the left child, okay, then check which side height is greater. The right side is height is greater. So this is the R is coming. The LR condition. In this case, we apply two rotation. First rotation we apply on the child node of this node which have greater than 1 balance factor. Okay, so this is 5. This rotation we will apply. So this is the first rotation, and this rotation will be anti-clockwise rotations. Okay, so we will just rotate this part in the anti-clockwise direction. Okay, so and we will consider this 5 position as a pivot position. So after applying the rotation, this 8 will be shifted at 5 position. Okay, and this 5 will be shifted to this downside on the left. Okay, so this 5 is shifted now this side, and 3 will be shifted one more position down, and this 9 will be shifted to one position up. Okay, we are just rotating this part as a one position in the anti-clockwise direction. Okay, so we are getting this.
Okay.
After first rotation. Now after that, according to the rule, yes, someone is asking.
Sir, why we are keeping 9? We can even take it to the left.
No, why
Right,
why 9
like-
will be shifted to the left or right?
Like I'm saying, for example, we can keep it at the place of 8, 9, and then shift it all in the left side of the tree.
No, we are not doing any random operation here. We are following some rule. Okay, so rule is says that first rotation we will apply on the child. Okay, and that rotation is actually shifted one position in the clockwise direction, say anti-clockwise direction. Okay, and this position will be considered as a pivot position.
Only one position we have to shift.
Yeah, one position we have to shift only the and this anti-clockwise direction.
Anti-clockwise. Okay, correct. Then
So
only.
always when we rotate, we always rotate only one position. So after rotation for this first rotation, we are getting this. Okay. So here you can see that second rotation we always apply on the node where we are getting this 2 balance factor. Okay. So this rotation is considered as a clockwise rotation. Now here is a problem. So because we have the right child 15, which is already connected with this 10. Okay, left child is also connected with 8. But when we just rotate this, so this is the pivot position now. Okay, after applying the clockwise rotation, so this 8 should be come on the position of 10. Okay, so that means this 8 should become at the top, at the position 10. And already so this we are rotating in that manner. Okay, so this is the pivot position, and we are rotating in the clockwise direction. So this 8 is shifted at the 10th position. Now this 10 will be shifted one position to the right down. Okay, 15 will shifted one position right down, and after that this 5 is already linked. Okay, so this 5 is connected with 8, so this will this will remain connected with the 8. So this 5 and this 3 will also remain connected with the 5. But there is one connection you can see, this where this 9 should we go.
Left of 10.
Yeah, so here we have to just apply some modification. So because in the remaining case we are just shifting one position in the clockwise or anti-clockwise directions. We are not just changing the reference of any node, child or left. We are not changing thing. But here there is one node which is connected on the right side of the 8 before, but after applying the rotations we have already connected this 10. So this 10 is now coming the right child of this 8. So how we will shift this 9. Okay, so 9 is greater than this 8. Okay, so in this part you can see that 9 is greater than 8. Okay, but if this 8 is shifted on the top position, so this means 9 should be come onto the right side. It cannot come onto the left side because 9 is greater than 8. So that means this 9 should be shifted in some position on the right side part. So we always add this 9 onto the what is the right child of this 8 now? 10. Okay, so that means this 10 is greater than of this 8. Okay, now this 9 will always be smaller than this 10 because this is coming onto the left part before. Okay, so this will be added onto the left of this 10 after rotation. So this 9 will be shifted here. So now you can see that binary search rule is still fulfilled. So this is one case you have to remember if you are applying this rotation. So this one case when you are getting this type of situation, if you are just moving this node which have already 2 childs onto the top, at the time you have to just shift on the right child on the left of the 10. This root. So this case you have to remember in 2 cases. Okay, so this is the one part. The similar type of situation can come on to the reverse type. Okay, right RL case. Okay, so how we will just handle this. So this is the way to handle. Okay, so when we are coming, when we are moving this 8 to the top, so now this 9 will become onto the left of the previous top. Okay, so now you can see that this is a now balanced tree. If this is the balance factor 0, 0, 0, and this is 0, and this is now 1 minus 0, 1, and what is the balance factor of 8 is 2 minus 2, 0. Okay, so similar type of situation may occur onto the reverse side. So reverse side means if we connect it like this, so 10, 15, okay, so like 12, 20, and here there is one node 5, and if we added like 11. Okay, so suppose this 11 is the last inserted node. Okay, and after adding this 11 we are getting balance factor 0, 0, 0, 1. Okay, 2 minus 1, 1, and here 1 minus 3. Okay, so 2. So you can see that this is unbalanced. And what is the type of this is? So right
Sir,
side.
why 12 is 1?
So what is the left side of 12?
2. 2 and 1. No?
Left height of 12.
1, 1. 1 and 0.
One height, no? If you're counting the
left side of 12 is 1 only.
Or right height?
Right height 0.
So 1 minus 0?
1 minus 0 is 1. Okay.
Okay. So now what type of rotations, what are the type of condition is this? So from 10, okay, so from 10, which side height is greater? Right side?
Right side. Right
now
side.
come to the right child. Which side height is greater?
Left side.
Left side. Okay, so this is the RL case. Okay, just opposite of the previous. Now in this case, first rotation you will apply on this part, and this is the clockwise rotation. And after applying this rotation, so 10 and 5, this will remain same. And here this part will completely rotated one position onto the clockwise direction. Okay, so
Sure.
this 12 will come here, and 15, and this 20, and this 11 will remain connected here. Okay, and second rotation you will apply, so this is the first rotation. Second rotation you will apply on this 10. Okay, and this is the anti-clockwise one. Okay, so here when you apply this rotation, so this 12 is actually comes on the 10th position. Okay, so 12 and 10 will come here, this 5 and 15 will remain connected in the same way, 20. Now this 11, okay, so this 11 will be shifted here to the right. Okay, so now you can see that the all binary search tree rule is still fulfilled, and balance factor is now become 0, 0, 0, and 1, 0, and 0.
So why don't we make it 11 to the left of 15?
No, 11 is smaller than 12. So how you can add into the left of 15?
Oh, yes. So that's the condition. Huh?
Okay, so 11 should become onto the left part of the 12.
Okay.
Okay, so these are the required, all I have considered all the condition now. So first are the 4 basic rotations. These 2 conditions are the additional conditions, so it will come during the process. If you know all this stuff, all these things, now you can make ABL tree. Okay, so I'm taking one example, one simple random example. Okay, suppose I have one random sample. Okay, so like 1, 8, 5, 10, 20, 30, 15, 12, 3. Okay, so I'm taking the random sequence 1, 8, 5, 10, this, and we want to create a AVL tree for this sequence. Okay, so you can also take some any random sequence and just try to create the AVL tree for practice. So here we will check, we will add first. Okay, so this one, now balance factor is 0. So this is the step-by-step process. Okay, so every step you will add one node into the previous binary search balance tree, and after that you will check the balance factor. Then if balance factor is not correct, then you will apply the rotations, then further process. Okay, so this is the step first. Okay, after that we will add 8 in this, so this will become like this 8. Okay, and after that 5, so this is also a balance because 0 and 1, so this is the second step. After that we will add 5, so 1, 8, and 5. Okay, so now balance factor is 0, 1, and 2. So after this, so in this case we are getting the unbalanced things. Okay, now which type of situation we are getting? So this is the R and this is L. Okay, so that means right side of the one and then child, left side of the child. Okay, so this is RL case. So first rotation we will apply on the 8. So it will so we will apply 2 rotations here. Okay, so this is the first rotations, and this is the clockwise rotations, and we will get 1, 5, 8. Okay, after that we will apply the second rotation here. Okay, and we will get 5, and 1 will move here and 8 will move here. Okay, so this is the final one after rotations. Okay, now this is the final one. We will add 10 in this balanced one. Okay, so I am adding on to the lower side, so 10. So 5, 1, 8, and 10, where 10 will add. So 10 is greater than 5, greater than 8, so 10 will add here. Okay, calculate the balance factor. So 0, 0. Balance factor for 8 is 0 minus 1, 1. Okay, balance factor for 5 is 1 minus 2, still 1. Correct, so that means no rotations required. After that we will add 20. So 5, 8, 10, this is the previous one. Okay, so we will always add the previous balance. Okay, so 20 will add, so 20 is greater than 5, greater than 8, greater than 10. So 20 will add here. Okay. So after that, calculate the balance factor 0, 0. So balance factor for this is 1. Balance factor for 8, you can see 0 minus 2. So 2. Balance factor for 5, 1 minus 3. Okay, 2. So you can see this condition here. We are getting this 2 balance factor on 2 nodes. Okay. So you will apply the rotations only this lower one part on this node. What type of this
RR.
balance? Okay, so this is R and R situations. Okay, to apply the rotations on this one rotation only and this anti-clockwise direction. Okay, so when you apply this, so 5 and 1 will remain same, and this 10 will be shifted up, and this 8 will shifted onto the left, and this 20.
Sir, how we have decided that here we will perform only one rotation, whereas in the previous one we applied two
So in RR type of case, this R case and L case, we apply only one rotation.
one rotation. Okay.
Okay. In R, L, and L, R type of situation, we apply 2 rotations. Okay. And also you have to just remember these things, which rotation we applied first and which node we applied. Okay.
Okay.
So this is the fixed rule of the AVL tree you have to remember. So here you can see that after applying this rotation on the lower part, if you calculate the balance factor again, so 0, 0, 0, and here is 0. So now the left hat is 1, right hat is 2. So 1 minus 2, 1. This is also reduced. Above 1 is also reduced. Now nothing need to do. Okay. So next node is 30. So 30 will be add onto the let me just add
Height of 20.
So 5, 1, 10, 8, and 20. Okay, and 30 will add. So 30 is greater than 5, greater than 10, greater than 20. So 30 will come here. Now, once again, you can see which type of situation is this. So first balance factor things. Okay, so 0, 0, and 0, leaf node. Okay, and balance factor for 20 is 0 minus 1, 1. Balance factor for 10 is 1 minus 2, so 1. Balance factor for 5 is 1 minus 3, right side 3. Okay, so this is 2. So you can see that we are getting this situation. Okay, so this is the case we have already seen. Okay, so here we have to think about this. So what is the case this
RR.
R? Okay, so first is right side from 10 right side. Okay, so this is the R situation. So here we will apply only one rotation on 5. Okay, and this rotation is anti-clockwise. So when we apply these rotations on 5, so this 10 will be shifted at the 5 position. 5 will be move one position onto the left down. Okay, so 5, 1, and this remaining will connect same way 20, 30. Now you can see this 8 part. Okay, so this 8 part will connect with the right of this 5. Okay, this is the additional condition which we have just discussed. Okay, if our node is moving to the top position, then if it contains the left child or right child, so here we will shift. So we are now shifting in that way. Okay, so we are getting this balance tree. So 0, 0, and 0, 0, and here this is 0 minus 1, 1, and this is 2 minus 2, 0. Okay, so we are getting the balance one. Next one is the 15. Okay, so 15 we will add in this. So 10, 20, 30, 5, and 8, and 1. So 15 is greater than 10, less than 20. Okay, so 15 will add here. So when we add this 15s, so 0, 0, 0, 0, all 0. Okay, no violation. So no problem with the 15. Then now 12. Okay, so when we add 12 in this balance one, so 10, 5, and 8, 1, and 20, 15, and 30. Okay, so 12 is greater than 10, it's lesser than 20, smaller than 15. So 12 will add here. Okay, after that, if you calculate the balance factor, so 0, 0, 0, 0, and this is 1 minus 0, 1, and this is 20 is 2 minus 1, 1, And what is the valence factor for 10? So left height is 2, right height is 3. So 2 minus 3 is 1. Still, this is balanced. Okay, so no problem. So now next node is 3. So 3 will add 20, 30, 15, 12, okay, 5, 8, 1. Okay, so 3 will add, so smaller than 10, smaller than 5, greater than 1. Okay, so 3 will add on to the right side. But if you see the balance factor, so 0, 1, 0, 0, 0. Now this is 1, this is 1, this is 2 minus 1, 1, and 3 minus 3, 0. Okay, no problem. So you can see, so during this process, we have added all the nodes. We found some unbalanced things in between, and finally we are getting this one. Okay, and this is a AVL tree, and this is the balanced one. So where if you calculate the height, so you will always get the maximum difference is maximum 1 in the height. Okay, so this is the process of AVL tree. So I hope this is clear. So you can practice after understanding this rotations. So maybe after solving 2-3 problems, you will clearly understand the rotations pattern. Okay, and you will get the clear understanding of this AVL tree, how we can create the AVL tree. Okay, so if we are finally, if we are getting this AVL tree, so this is approx equal, approx balanced. So we can get benefits of the this log n things. Okay, so log n in searching, log n is insertion, log n is deletion. So all operation can be performed in the log n time if we have the balanced binary search tree. So any query in this AVL part? Okay, so just practice some on the sub problem. Okay, so there is no need to wait for the problems from our side. You can take any random sequence. Okay, and there is also many sequences available on the internet. You can just check some sample problem on the AVL tree. After that, you can compare
whether this session is recorded, sir?
Sorry?
Whether this session is recorded?
Yeah, this is recorded on the YouTube as well as the recording we are doing. Okay,
Link
this is
not given in the calendar.
Yeah, calendar it is not added in channel. It is there. After this session, I will add this link in calendar as well.
Okay.
Sir,
I could not.
why do we balance all the nodes, sir?
Sorry.
Why do we balance all the nodes the way what we are doing now?
Yeah, why we are balancing this?
Yeah.
Yeah.
You said BST is mainly for easy sorting and
not
the
sorting,
speed,
not sorting.
and the speed searching for easy search and
yeah, actually
the speed of search is log n times, no?
Yes, actually BST is a data structure which contains the data. Okay, and why we are storing data? Because in future maybe we will use that data for some purpose, for a specific purpose. So at that time maybe we have to access some data from our data structure. So that access operation, that searching operation, that should be performed fast.
That's for efficient searching operation only.
Yeah, efficient searching as well as insertion.
But BST itself is efficient, and why do we really need to balance?
No. Normal BST is not always the efficient if it is not balanced. So I have given one example. Na? If suppose if we are receiving some data to insert in the binary search tree in this way, like so 1, 2, 3, 4, 5, 6 like this. Okay, suppose if data is coming in this order.
Okay.
And we are storing this data in our binary search tree. So this 1 will be added at the top, 2 will be added on the right, 3 will be added here, 4 will be added here, 5 will be added here, 6 will be added here. Okay. So now this is a binary search tree because we are adding the node according to the binary search property, but all nodes are connected onto the right side.
Yes.
Okay. So the height is become now equal to n.
Right.
Both are same. So now you cannot take any benefits for this searching operation.
Okay.
Okay, you have to traverse all the nodes onto the right. So all n nodes you have to traverse. So it become a linear operation.
All right. Okay.
Okay, so because of that, we want to make this as a balanced binary search tree. Then we can achieve this log n complexity for operations.
Okay. Okay.
Okay,
All
so
right.
this is the required thing for the binary search tree.
And what does AVL stands for?
And I
Is
think
it
Veleski.
any expansion there? Is there any expansion there?
Yeah, this is no meaning. This is the name of this scientist. Yeah.
Okay. All right.
So Veleski, Adam Veleski. Yes, I think some this name.
Okay. Somebody's name.
Yeah, name. Who actually developed this? The name is based on the yeah, Adelson, Veleski, and Landis. Yeah, correct.
All right, sir. Thank you.
Okay.
So just to correct my understanding, so wherever we are saying LR or RL, so the rotation operation we are doing from the right side. That is, if it is RL, we are performing the rotation for L and then for R, right?
No. This is the understanding of the this binary search tree height. Okay, so but rotation is the different way. Okay, so if you see the LR, okay, so this if you see this LR, so this is just to understanding the type of the unbalanced binary search tree. Okay, but after that, what we are doing, we are applying first rotations on the child node, and this is the anti-clockwise. So there is no relation. We can you can also make some relation. So suppose you can just consider that this is on the child and rotation is the anti-clockwise.
Right. No. When we say LR, L is like for the top node and R is generally for the child node, no? Because that is how we are reading also LR or RL.
Okay. So the what you're okay. So suppose if we are getting some unbalanced tree, so where we are getting the balance factor greater than 1, okay, from that node we will check this. Okay, and which side height is greater from this 10? Which side height, left or right?
In this case, it is left.
Left. Okay, so because of that, we are getting the first L. Okay.
Right.
After moving to the left child, okay, so just left child, okay, not the lower one, okay, just direct connected left child. And from child, just see that which side height is greater again.
Which is in the case right side.
Yeah, right side. Okay.
So now my question is, when it is right side, so first I need to perform the rotation for the R part.
Child node. Not R part. Yeah, you can see that from this child, the complete part which is connected below this, not only the R part.
Okay.
We cannot say that. Okay.
Okay, got it. Understood.
So which part connected below this 5 node, all will be considered for the rotations.
Understood.
Okay. And this rotation will be happen in the anti-clockwise direction. After that, on the 10, we will consider the complete part which is connected below this 10. And we will rotate onto the clockwise direction. So we cannot relate in that way.
Sir, actually, visually we can say that it is anti-clockwise, clockwise, but programmatically how?
Yeah, programming. If you see the implementation, same things we are doing in the implementation. So let me just show you. So for the implementation, this rotation is just happening by the changing of this parent address and this things. Okay. So let me just show you left rotate and right rotate. Yeah, so these are some operation here. It is given so insert operation, rebalance things. Yeah, so you can see that this is the insert operation. So this implementation is given on the GitHub notes. I hope you know, and sir is also explained. So this is the final implementation overall. Okay, so this is the simple insert operation. We are adding new node by the same insert binary search insert tree method. Okay, so we are checking the value is smaller than the current value, then we are moving to the left insert left side. Okay, and in that way, once we are getting the empty, then at that time we are connecting that node. So this is the insert operation. After every insertion, okay, so when the insert operation is completed, the next operation is the rebalance operations. Okay, so after that we will check this rebalance operation, and we are also calculating the height of every time for each node. Okay, self dot height for each node we are calculating the height, and inside the rebalancing, so rebalancing, you can see that we are following the similar things. So first we are calculating this h left height and right height difference. If it is greater than 1, so we are applying this some process. Okay, so this is the first process. So we are not here calculating in the similar way which we have just explained. So we are not calculating the absolute value here. So this first value we are checking the top node where we are getting the higher balance factor, which is greater than 2. After that we are moving to the child node. Okay, and moving to the child node, we are checking the second condition, left child height is greater than to the right child height. Okay, so this second condition is actually handling to the RR. So first, suppose we are getting R. Okay, R case. Second condition, what we are getting, R or L. So that is identifying by this second condition. So this, if this is
So the
greater,
line what you highlighted 78, it is, if it is true, it is L, no?
sorry, L HL
78.
minus, no, 1 second. HL minus HR is greater than 1. Okay, so left height is greater than. Okay, so here, so
LL.
this is the case, LL case.
LL.
This if this case is satisfied, this is the LL case. Okay, if this is not true, then if this is true, so this is the LR case. Okay, if this condition is true and this below condition is true, so you can see that we are applying 2 rotations here. So this is the LR case. So this is checking the R condition inside the L condition. Okay, and when we are getting LL, we are applying only 1 rotation. This is the right rotate. Okay, and when we are getting this LR condition, we are applying this 2 rotations. First is the left rotate and second then right rotate.
So when it is LR, first we'll do left, then we'll do right.
That means we are going to the left child. Okay, and we are applying this after moving to the left child. Okay, then we are applying left rotate. Then we are applying the current right rotate on the current node.
Yeah, sir, 82 is what is not clear. Actually, 81 is clear, but what is this?
This one?
Yeah, this one.
So what happening? Let me just clear this thing 1 second. So this is the part of code. Okay, suppose if we are getting this type of situation, so we have node 10 and this 5, this is 1. Okay, and we are getting this type of situation, and here HL. Okay, so we are checking, for example, this node. Okay, so HL, what is the HL height is 2 and R is 0. So difference is coming 2 here. Okay, so this condition is 2.
Yes.
HL minus HR. After that, we are just moving to the left node. Okay, so this, you can see that self dot left height. Okay, so that means we are first coming on this left node. Okay, and from this node we are checking what is the left height of this. What is this left height? So left height is 1 here. Okay, and this left height is greater than the right height this side. Okay,
so here when we say self dot left height, are we checking the height of 1 or 5?
5. So self is now pointing to this 10. Okay, when we are saying self dot left, so that means we are pointing here. Okay, and this left height is indicating what is the left height of this 5.
Okay, it is not pointing to the direction, it is just pointing to the, for the height purpose.
Yes. Okay. So here actually now in this case, by satisfying this condition, we know that this is the L condition. Okay, first L. For checking the what is the next, this is R or this is L. Okay, to check this we are just checking by this 2 condition. Okay, this 2 condition. So the first, if the first condition is satisfied, so first condition is saying that if left height is greater than the right height. Okay, so if this height is greater than to the right height, so this condition is true, that means this is the case of LL. Correct?
Yes, sir.
Then we are applying this self dot right rotate. So self means we are here and we are applying the right rotate.
Correct.
Okay.
Yeah.
The second condition is if left height is smaller than the right height. So that means this left height is smaller than the right height. So that means some node is connected in this manner. So 10, 5, 8 like this. Okay. So first we are getting L by the first condition, and second case, so right height is greater than now the left height. Okay. So this condition is now true. Okay. In this case, you can see that first rotation we are applying self dot left. So first self is pointing to this self dot left is coming here. Okay. And we are applying left rotate. So left rotate is performing this anti-clockwise operation here. First operation. Okay. Sorry, this one, above one. So this rotation is happening on the left child of this 10. So we are getting this similar way, this 8 and this 5. Okay. After that, you can see that self dot right rotate. So self is pointing to this 10. So we are applying right rotate. So right rotate is clockwise rotate. So you will get this 8, 10, 5 like this. Okay. So this part is handling L, L and LR situation. Okay. The second part, you can see this second part. Okay. This is handling R or RL case. So same things. The difference is different. If you are getting HL minus HR is less than equal to -1, that means opposite. Okay. Same things for the RL. So this is the R case, first R, and this is the R case, and this is the L case.
Yeah, got it. So
Okay.
can you go to the code once? In that, if you scroll up, scroll up.
This rotate.
Yeah, there is one max value. If you can,
Where?
I think in the insert. Yeah. Self dot height is equal to 1 plus max self dot left height and self dot. What exactly mean? I mean,
Yeah. So when we are performing this insert operation, okay. So we are just incrementing the height of each node.
Okay, incrementing the height. Yeah, updating the height basically.
Updating the height.
Okay.
In later we will calculate the difference, no?
Yeah. Correct.
So because of that, we are updating the height.
Got it.
Operation. So these are the rotations. So in rotations, you can see that we are just changing the pointers, or we are changing. So we are performing the same operation, but to implementation part, we have to change the reference after rotations. Okay.
This is similar to the linked list what we studied.
Yeah. So this all things are actually connected in the same way, linked list way. Okay. We are just changing the right child, changing the left child, changing the parent things. All things we are just updating in the similar manner. Okay, if we need, so if we are performing some rotate, so maybe sometimes we need to create new node. Okay, if we are rotating, so this LL case in this case. Okay, so if we are applying this rotation, so 10, 5, 1. Okay, and when we are applying this rotation, so this position is already there. So we can simply copy this data at this position. Okay, so this 5 will separate here. But to to add new node here on the right side, we have to create one new node. So we at that position we have to just create new node first, then we will copy this 10 here, and this node is also there. So one will be copy into this. So one will copy to this location, and this place is empty. Then now we will remove this. So we will just remove this connection. So in that way, implementation way, we have to just change the things, connections, and we have to create some new node for the rotations. Okay, so this is the simply linked list process. We are creating new node, we are connecting by the reference on the left child or right child locations. Okay, so this is the same. If you just take some example and just go step by step, you will get the clear code what we are doing. Okay, this left rotate and right rotate. Okay. So if the concept is clear, so then you can understand the implementation part. First, you should understand the rotations or all these things. So I hope this ABL part is clear.
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
So next, yeah, Subramaniam. yeah, I hope some practice is required after this. Okay, so if you are getting some idea, some example you have to take in, you have to apply the rotations on the example, then you have to maybe 3-4 problems you have to solve to get the clear things. Okay, but maybe you
OPP,
cannot recall the things.
OPP, OPP, you will get an AVL problem, sir.
No, that type of high level, this very big type of implementation we generally not gives. Okay.
Okay.
We also know that you have only 2 hours and you have 4 problems. So how you can write that level of code in 2 hours? Okay. So no, yeah, but you should know the concepts.
Yeah, okay, sir.
Okay, because in this quiz paper, some questions may be asked from this type of some sequences given. What
Okay.
is the correct AVL tree? Okay.
Got it.
So yeah, next part of this beak is the this greedy algorithm. So according to the name greedy, so what is the meaning of greedy? Means greedy choice. So it every steps we always select the maximum optimal things or based on the greedy current decision. So that means you have already learned some greedy algorithm, but at that time you don't know maybe what is greedy. So if you know that this Kruskal algorithm, okay. So when we are just applying the Kruskal algorithm, if you remember that, so our main purpose for spanning tree was to get the maximum minimum. Okay, suppose we have graph like this, A and B, C and D. Okay, and our edges are like this, so 10, 5, 3, 1. Okay, so in according to the Kruskal algorithm, we just arrange this edge in increasing order of their weights. So our first edge is like B, D, that contain 1, and second edge which is greater than is C, D. Okay, 2 weights, and this AC contain 5 and AB contain is 10. Okay, so first this is the process, we collect the edges by their weight in the increasing order, and after you can see that we always select the edge with the minimum edge, because our main goal is here to getting the minimum sum. So we want to just convert this graph into a tree, so where all vertex should be connected, okay, with the minimum total weights. Okay, so this is our main goal for the minimum spanning tree. So we are starting this process, and we are always selecting the edge with minimum weights. So this is the greedy choice actually. So in the when we are solving this problem, at every steps we are selecting the greedy choice according to our goal. If we are just solving, if we want to find out some maximum things, we are always selecting the maximum things on the each steps. So here we are selecting the edge which have the minimum weights at each step. So first we will select, so suppose this is the disconnect component, so A, B, C, D. Now we are selecting the edge which contains the minimum weight. So this is the first greedy choice we have. Okay, so this is BD, we will connect in the spanning tree. Okay, and 1. After that, in the second position, we are collecting the next smallest edge which is not creating a cycle. So this is CD. Okay, now 2. Next step, once again we are getting the next minimum. Okay, so this is 5. So 5. This is not creating a cycle. Now next level we are adding the next minimum. Only 1 is remaining, 10, but it is creating a cycle. So we will not select this. So you can see that we are getting a spanning tree, and the weight is 1 plus 2 plus 5 is 8. And this is the minimum spanning tree, where the total weight of the edges is smallest in the all possible cases. So there are multiple cases to create a spanning tree, but only this contains the minimum total weights. So here in each step we are selecting some greedy steps to find out the overall optimal solution. So this is called as a greedy approach. So here similar to this Prim's algorithms, that is also follow this, similar to this Diest algorithm also follow this greedy approach. So when we solve the Diest algorithm to find out the shortest path, so same things. When we just visit the next node, so we always select the node which have the smallest distance from the source. So at that time we are selecting because our main goal is to find out the shortest path with the minimum distance from the source, and each step we also consider this rule. Okay, so that means at each step we are just taking the greedy decision. So so this is strategy. Sometimes works, sometimes not works. So this is
What
not
is that statement, sir? Greedy strategy needs a proof of optimality. What do you
yes.
mean by that statement?
This means sometimes maybe you will feel that your greedy strategy is correct, but this is not always true in the case of greedy strategy. So some proof is required to find out that your greedy approach is providing the overall optimal solution or not.
But you are telling that once you have chosen, it is chosen, but you are not going to going back. And again, you are telling me
Yes,
there is no
correct. So
optimized.
we never look back. Okay, we are always selection greedy things on the each steps. We never check back what happened in the back. We are getting overall optimal or not. Okay, so some proof is required. So in this case, so this Kruskal algorithm is actually proved that this is providing the minimum spanning tree. So because of this algorithm, it is now become standard algorithm. So similar things. So I'm just explaining one problem. Okay, so let coins problem, if you know that. So suppose we have some coins like 10. One second, not 10. Okay, so 8, 6, 5, 1. Okay, suppose we have some coins with the value of 8, 6, 5, 1. Okay, here I'm taking another example also. Let first discuss this. So like 10 and 5 and 2 and 1. Okay, suppose we have this set 10, 5, 2, 1. We have infinite number of coins with the value of 10, 5, 2, 1. Okay, and our goal is here to create 30. Okay, we have some amount 30, and we want to achieve this amount by minimum number of the coins. How you will get this? What approach here you are finding to solve this type of problem?
You will take the highest one first.
Highest
Start with the minimum.
value.
So we can sort.
So this is already sorted. Yeah, first step you can perform the sorting. Okay, so you are getting this 10, 5, then 2, 1 in the sorted order, correct?
Yeah.
After that, you are saying that you will always select the coin which have the highest value. Okay, and here each coin have the infinite number of coins. Each value have the infinite number of coins. So first you will check the number of coins with the 10. So to achieve this 30, so you can use 3 coins of 10. 30, and this 3 is the answer. So that means minimum 3 coins is required, correct?
Yes.
Or you are getting any other answer, other optimal answer?
So can you explain once again, sir? I didn't get this.
So first thing, we have some value 10, 5, 2, 1. Okay, so we have infinite number of coins with these values 10, 5, 2, 1. Okay, we have some amount a equal to
This
30.
infinite value is for this. The infinite values for these numbers. What does this mean? Like 10.
Infinite means we have infinite number of coins of 10 values. Okay, infinite number of coins with 5 values. Suppose if we want to calculate the 100 amount, so we can take 10 coins with the 10 value directly. Okay, so there is no limitation of the frequency of the this coins. So you can select any number of counts of the one particular value coins. Okay, so this is the meaning of infinite. If you need 100 coins of 10 value, you can select. Okay, suppose if you want to find out the 25 amount, so how you can achieve this? So first you can select 2 coin of the 10 and 1 coin of the 5. Correct? Total coin number is 3. So I think this is clear problem.
Yes, sir.
So here maybe you are feeling that if coin is given, suppose we are giving this coin sequence like this, so 2, 1, 5, 10. Okay, this sequence in unordered situation. So first operation you are performing, sort these coins. Okay, so sort, after sorting you are getting 10, 5 and 2 and 1. And after that you are applying, simply you are applying the algorithms. You will always select the highest coin value first to achieve the amount. So suppose 25, first you will try to fulfill this amount by this 10 coin. Okay, so you will try
Are we getting the maximum or the minimum?
minimum number of coins.
Can you please scroll up?
We want to find out the minimum number of coins to achieve this amount.
Now, in the first example of the
No, I am not discussing of the first example.
No, just scroll down, please. No, hold on, please. Here. Now, when you really took up this example, A, B, C, D, you just started with the lowest number, no?
So at that time we have some different problems. We want to. So here, okay. So what you actually
You
here
started with the last one. If you really connected, it becomes a cycle. So we dropped it, and then now A, B, C, D is the minimum.
Here actually what is there here, our goal was to find out the total distance minimum, this total distance minimum, okay, to connect it to the all nodes.
Okay, now what we
and at that time we have the edge weights and we are adding finally total edge weights. But here we have the amounts, but we are calculating the number of coins, not the amount. Okay, so this problem is different. Here some amount is given, number of coins is given with the different values, and our goal is to find out the minimum number of coins
to connect all the vertices, is it? All the nodes.
Not 46. This is the different problem to achieve the amount. Okay, here this is not the edge and vertex. This is we have some coin. Okay, 2, 1, 5, 10. Some coins are given. Each coins have the infinite number of frequency, and we have some amount is given, like 25. Now our goal is to achieve this amount with the minimum number of coins, not the value or anything. Okay, coins we are counting here.
Okay, we are given 4 denominations and asked to really find out the minimum number of coins.
Yeah,
to make it to 25.
Yes.
So that's the problem statement here.
Yeah.
Whereas earlier you said you asked us.
That is the critical that minimum spanning tree problem. That is the different. Okay. Okay. So to solve this problem, first things comes in your mind, like first sort this. Okay. So 10, 5. Okay, and 2, 1. Okay. And what you will do? First, you will try to fulfill by this 10 coin. Okay. So how much amount you can complete by this highest number of value coin? 10. So maximum, 2 times you can just contribute. So 10 into 2, you will get 20. Okay. So 10 into 2, 20. So that means 2 coin is required. Now still 5 is remaining. You cannot fulfill this 5 by this 10 coin. Okay. So this is higher amount. Now you will move to the second highest. So 5. And here you can see that you are achieving this remaining 5 value by this 1 coin of 5. So 1 into 5, 5 into 1 by 5. Total is 25 and total number of coins are 3. Correct?
Okay.
Okay. So if you solve this problem with some example, so maybe for the same number of coins, if you want to just achieve like 23, how many coins are required?
2, 10, 1, 2, 1.
So 2 into 10, 20, and this 1 into 2, 2, and 1 into 1. Correct? I think you are solving in this manner.
Yeah.
23 and total coins are 4. So this so no optimal solution for compared to this. You cannot achieve this amount in less than 4 in any way.
What way it is greedy? It is just normal way, no?
No,
Why
this
do you
is
call it
greedy.
as
No,
greedy?
this is greedy because you are always selecting the first highest. Because here you want to complete this 23 amount by the minimum number of coins, and you are selecting the highest value coin first. So here every steps you are selecting the highest first. If it is not completed by the coin, then you are selecting the second highest, then third highest, like this. So this is the greedy things. Okay, you are trying to fulfill in the by the highest value in the every steps. Okay, so this is the greedy things. In that way, maybe you are thinking that this approach is correct.
Yeah.
Okay, but some counter example I am giving now. So now this coin sequence is given 8 6 5 1. Okay, this is already in decreasing order, no need to sort. Now one amount is given like 11. 11. Okay, now you will apply the same logic here. You will select this by the first highest coin. Okay, so you will get 1 into 8. Correct? And after that, you are getting 8 value. Remaining value is now 3. Okay, now you need 3 into 1. So you will get 3 and you are getting 11. Now coins are total 4. So you are applying the same.
But
you are
I
applying
can select 5 and 6.
Yes. So you are applying the same approach which we used with the previous example, which was looking fine, but here this is the another part 6 plus 5. Okay, so one coin of the 6 and one coin of the 5. You are getting 6 and 5, and you are getting 11, and the coin is 2. So this greedy approach now become fail. Okay, so because of that, greedy approach looks correct in the initial time, but we need to prove that it will always work by some counter example or these things. Because of that, professor is discuss these things. So during the explain this interval scheduling or these standard algorithm which can be solved by the greedy approach. Okay, so so greedy is not always good. Okay, so compared to the greedy approach, you can use the dynamic programming approach. So dynamic programming approach is better than the greedy, because greedy maybe fail in some case if maybe you are not thinking some counter example which maybe it fail. So some proof is required, some standard algorithm you can use which is already proved. So because of that, greedy. So here this is given now in the first statement, need to make a sequence of choice to achieve a global optimum. This is the things. At each stage, make the next choice based on some local criteria. Never go back, because we cannot move back to change the decision. Because if we are selecting at each level, we are selecting the greedy choice and we are getting the optimal solution. So we cannot change the previous decision in this approach. And sometimes it provides the optimal solution, but not always. So that last statement is given. Greedy strategy needs a proof for optimality. Okay, so example is given: Dijkstra algorithm, Prim's algorithm, Kruskal algorithm, and this interval scheduling, minimized lateness, Huffman coding. These algorithms are discussed in this week 7. So this is one scenario which is discussed: interval scheduling. So what is the scenario is some online lectures. Some IIT Madras has a special video classroom. One classroom have for delivery the online lectures. Different teachers want to book the classroom, but nobody can take the lectures on the same time. So okay, so that overlap cannot be happen. So slots may overlap. So not always all bookings can be honored. Choose a subset of booking to maximize the number of teachers who get the use the room. Okay, so problem, I think if you have seen this lecture, so suppose we have only one room and some request we have. Okay, so suppose A is given like the request, he suppose with time is given also. Okay, so 1 to 2, so this value is given as a starting time and end time. So A want to conduct the lecture on 1, starting time at the 1 to 3, like this. Okay, so this is the start time, this is the end time. Okay, B is want to take like 2 to 4. C want to take like 12, or we can just take like 5 to 6. Okay, D 4 to 6. E 6 to 7. Okay, suppose we have some request for the same room for the start time and end time. Any lecture can be performed if it is starting from the, suppose if any lecture is starting from 1 and ending on 2, so another lecture can be start from 2 to like this 3. Okay, it cannot be before that. We cannot start like this, so 1 and 3, and we cannot start 2 to 4 like this. Okay, so this is the overlapping. This part is the overlapping. We can start at the finish time of the other, so without overlapping. So how many maximum allocation we can do here for the classroom? So this type of problems, if we have one classrooms, we have some request where the start time and end time is given, so how we can allocate the maximum teacher to take the lectures in the room? Okay, so this type of problems may be create for the many real life scenario. Okay, for the machine, if any machine is performing some job and we have the request of jobs on the some specific time, so how many maximum jobs we can perform on the machine? So this so many types of real life problems can be created based on this okay, interval scheduling concept. So here, so if you just try to solve this, you can just randomly check what type of how many maximum you can achieve. Okay, so 1 2 3. So if you perform, suppose we have this line, suppose we have one line. Okay, where the timing is started like so, 1 2 3 4 5 6 7. Okay, I'm just messing number 2 3 4 5 6 7. Okay, so first A request is like 1 to 3. Okay, so I'm just marking some requests. So this is the A request, and B request is 2 to 4. So B request is 2 to 4. Okay, this is B, this is A, and C request is 5 to 6. So 5 to 6 C, and D is 4 to 6. So 4 to 6 and D. E request is 6 to 7. So 6 to 7. E. Okay, so this is the request duration of the classroom. So you can see that overlapping is happening with A, B, then C, D. Okay, so how you can achieve the maximum number of allocation?
ADE.
So you can select either A, okay, A, after that you
D.
cannot select B, then you can select D and E. Okay, another choice is also happen like A, C, E. This is also possible. Similar B, D, E, B, C, E, like this. Okay, so maximum you can, here we are just counting, we are not counting which jobs will be performed, we are counting maximum number of jobs will be performed. Okay, so if we are calculating which allocation we can do, so there is multiple answer for this, but maximum count allocation, maximum number of count, that will be remain same, that will be the fixed for this problem. Okay, so for this problem we are counting the answer for maximum number of allocations. So how many number of allocation we can do which is maximum in this situation? So that answer is 3 for this. So how we can solve this approach, how we can solve this type of problems by the algorithm, this interval scheduling algorithms. Okay, so according to this algorithms, so we have the time, start time and end time for each jobs. Okay, so what you can do, you can sort all the jobs which based on the end time in increasing order. So this is the first step. First sort the job in increasing order. So here A, B, C, D, E, F, we have 5. So So ending time, based on the ending time. So we will just only look the ending time. So, and we will sort the jobs based on the ending time. So which job come first? So 3, 4, 6, 6, 7. Okay, so already it is sorted. So A and B and C, D, E. We are getting this order. Okay, A, B, C, D, E. So this is the first step. After that, what you will do, you will select the first job. Okay, so this, you can see that take the interval which has the earliest finish time. So you will start from the first job, and after that you will always check if the current this current request starting time is greater or equal to the previous end time, then you can select, otherwise not select. Okay, so in that way you can find out the maximum things. Okay, so if in this process, so the same for, I'm writing again, so A, B, C, D, E. So one, this is 1 to 3, 2 to 4, 1 to 3, 2 to 4, and 5, 6, 4, 6, so 5, 6, 4, 6, and 6, 7. Okay, so this is already in increasing order of the end time. What we will do, we will select the first. Okay, so we can select the first directly, and when we complete this first, after that we will check the second. We will always check the second start time, and we will compare this start time with the previous selected end time. If it is start time is smaller than compared to the previous end time, then we will not select. If it is equal or greater, then we can select. Okay, so here you can see that the start time of the B is smaller than the 3, so we cannot select this. Okay, move to the next one. So this 5 is greater than the previous selected end time. Yes, correct, so we will select this. So here now the what is the end for this is 6. Now we will compare by this previous selected, last selected. Okay, now 4. So 4 is smaller than the 6. Okay, we cannot select this. And 6, yeah, 6 is equal to 6, we can select this. So in that way, in this process, we can count the number of jobs we can perform. So this 1, 2, 3, total 3 jobs we can perform. So this is the simple algorithm of the interval scheduling. Just first step is arrange the request by the ending time in increasing order. After that, compare the start time to the previous selected end time. If it is smaller than, then not select. If it is greater than or equal to, select. Okay, in that way you can count the maximum number of allocation. Okay, so in that way maybe you will get only one selection. So here you are getting A, C, and E. So A, C, E, we are getting A, C, E by this process, and count we are getting 3. So this count is actually maximum. Okay, this answer is correct if we are only counting the number of allocation, that is 3 fixed. But we cannot decide that this ACE is the only selection. Okay, we have already seen that this ACE, ADE, BDE, BCE all are the possible selection with the same 3 count. Okay, but algorithm is implemented in one fixed way, so it will always provide one fixed answer for this. So this type of problem we only used to just find out the maximum number, minimum number, this type of information. Okay, one possible answer you can just return, but not the all possible answer.
Suppose there was one more allocation like F from 7 to 8, then that would have also been included. It would have been compared with the previous.
Yes. So, suppose we have like F and 7 to 8 you are saying. So you can see that this is also coming in the increasing order, 7 and 8. Okay.
And this starting time of F will be compared with ending time of E.
Yes, last selected one. So last selected one was E. So this is 7. So the 7 will compare with 7, and this will also select.
Okay. Sir.
Okay. So regarding this overlap things, so some information will be given to you. What is the overlap condition? So sometimes this overlap condition is given in that way. So any activity can be started only after the ending time. Suppose one activity is starting 1 and completing at 2. So second activity can only be start after this 2, not including this 2. Okay, like 3 to 4. So they are considering, so suppose if this information is given, then they are not this, they are also considering this overlap 2 to 3. So this 2 is also overlapping in that way. Okay, so based on the problem statement, what condition is given for the overlap time, so just decide to that how you can select. Suppose if this condition is given, any activity can be start without overlapping if this is starting after that of the finishing and ending time of the previous one. So at the time you cannot select this 7 and 7. Okay, at the time you can only select if any value is greater than with the previous one. So based on the problem statement, just read these things. What is the overlap condition is given? So overlap condition, they are considering the equal value at the overlap things, or they are considering the equal value at non-overlap things. Okay, so we can just solve this problem. So algorithm is simple. Here you can simply see the algorithm steps. So sort all the jobs based on the end time in increasing order. Take the interval which has the earliest finish time. Repeat next 2 steps till you process all the jobs. So eliminate all intervals which have start time less than selected intervals end time. Okay. If interval has start time is greater than current intervals end time, at it to set and set current interval to the new interval. So this is the same step we have just followed. We what is the current end time is if we are selecting this A, so current end time is 3. So we will just always compare with this 3. Okay, if we find out the current selected interval C, so we will always compare the next one with this 6 last current selected. Okay, 6. So these things we are doing. So in that way you can find out the maximum number of allocation. So this is the algorithm of interval scheduling, which we discussed in the first lecture. So now you can write the code for this. So this is the basic steps. If you know the steps, you can simply write the code for this. Okay, so here you can see this activity problem is given. So problem statement you can see. This is the question which is asked in the one quiz exam. Okay, so this type of problem you can assume that this type of problem can be asked in the exam. Okay, in the table below we have 8 activity corresponding to start and finish time. It might not be possible to complete all the activities since their time frame can conflict. For example, if any activity start at time 0 and finish at time 4, then other activity can not start before 4. So here condition is given for the overlapping. Okay, so any activity cannot be start before 4, but it can be start at 4. So that means they are not considering the equal value for conflicting. If any activity is ending at the 4 and another activity can start at the same time, so that is not conflicting. Okay, so based on this condition, just make your condition. Okay, so here first thing is the end time is given, finish time is given. So first step is sort this activity according to the finish time. So this A first will come at the first, then B, then D will come.
C will come first, sir.
No. C end time is 6, but
Exactly.
after that you can see that 4 and 5 is also.
End time, not the start time.
Yeah, end time, finish time.
Right.
Okay, sort the activity based on the finish time. You can, so you can, so another greedy approach you can think about, like if you sorting the activity on the start time. So what is the problem with this is, so like for the same example, I'm taking another example. So maybe what happen is, so like 1 to 4, B 2 to 3, and C like 3 to 4, D 4 to 6, like okay.
Lead to suboptimal selection.
So suppose if you're sorting the activity based on the start time, okay, start time. So what we'll do, so you will always select this first. So A 1 to 4. Now you cannot select this B, C, and you can select only 2. This one. Okay, and you will select D. So A and D only you can select. But what the another possible answer is, if you select the B first, okay, so B is starting 2 and 3, then 3 and 4 and 4 and 6. So you can also, optimal solution for this is B, C, D. Okay, but by this approach, if you are selecting the activity based on the start time, then you are getting, you may get the incorrect answer. Okay, so always sort the activity based on the end time and just apply the rule, then you will get the optimal answer. So this is the interval scheduling, and next one is the minimize lateness problem. Okay, so here we want to minimize the lateness problem. So first thing is the this should be clear what we are talking about here, minimize lateness. So this thing is also not clear for many times. So
Sir, I didn't get what you was explaining the that sheet.
which one, which problem?
The notepad one.
This one?
Yes.
I have discussed the interval scheduling problem.
Yeah, you said that you said just we need to sort in the last.
Huh.
The
So
18 BCD thing.
yes, so what we are just trying to do is we are just trying to change the approach. For this example, what we are just trying to sort the activity based on the start time, and then we are selecting the activity. So we are just checking that we are getting the optimal answer or not. So this is just counter example we are trying to solve by the another approach, but here by this approach we are not getting the optimal answer. So here you can see that we have sorted the activity based on the start time. Okay, 1 2 3 4, and then we are starting selection. So we are selecting A first. So A selected. After that, this activity is finishing at 4. We cannot select 2 3, then we can select D. So we can select only these two activity. Answer we are getting 2. But
Yeah,
the
okay,
correct
got
optimal?
it, sir.
No, this is not the optimal answer. We can select B C D 3 count. Okay, so because of that, the greedy approach is not always correct, which because of that we are mentioning this. Sometimes we think that the approach maybe work on the some examples but not all work on the all examples. Okay, all cases. So that required the proof. So because of that, the standard way is to solve this interval scheduling by sort the activity based on the end time. So if we sort this activity based on the end time, so this 3 will come first, then 4, then 6, like this. Okay, so
So
B,
when we are sorting based on the end time, then too it is a greedy algorithm only, right?
that it's still it is greedy algorithm, and also you will get the optimal solution. Okay, so by the ending times sorting this process, so B will come at the first. Okay, so 2 to 3. Okay, then we can select this A because A is ending with this 1 to 4, then C 3 to 4, and then D. Okay, 4 to 6. Okay, you can see now we are sorting the activity based on the end time. Now if you start the activity from the first, so we will select B first. Okay, so B will select. Now end time is 3. When we check for the A, so this one is less than 3, we cannot select. Okay, if we will check the C, so C is the equal, so we can select this. Now end time is 4. If we check this, start time is 4, which is equal to end time. So yeah, we can select this one also. Okay, so BCD. Then we are getting the optimal answer.
Yes, got it.
Okay, so this is the interval scheduling problem. Next problem is this minimize lateness problem. So what is this minimize lateness meaning here? I just take this example. This term is actually confused sometime. So same things, we have some jobs. Okay, we have some jobs. So an ID is given. So ID is given jobs. Okay, and one another thing. What is the things? Start time job setting. Okay, so time, finish time. Okay, second value is 1 second. Okay, deadline is given, and okay, cost is given. So okay. So what information is given here? First value is the ID representing. Okay, so this ID. Second value is representing like a total time. So time required to complete. Okay, time required to complete. So we can say that first time, and next value is given deadline. Okay, so here like jobs is given by the ID, so 136 and 229 318 and 449 5 3 14 and 6 to 15. Okay, so the problem is given like this. So we have some jobs. Okay, jobs ID are given 1 2 3 4 5 6. We have some worst time, that means time required to complete that job. Okay, so 3 times is required to complete the ID one. Okay, 2 times is required to complete the second job. So this is the time required to complete. This is the deadline time. Okay, if any activity, suppose if we are starting any activity from 0 time, so that means the activity, or we can say that the 1 time. So first activity should be complete in the 6th till 6th time. Okay, so this is the first and this is the 6th. This is the deadline for the first activity. So it will take 3 times. If it is started from 1, it will complete on the 3. Or we can start, this is 0. So 0 plus 3 is 3 now. Okay, so that means the deadline is given 6, and if we start this activity from 0 times, it will complete at the 3 time, because it takes 3 times. Okay, so that means if it is completing before the deadline, so this is the good things. So sometimes the problem is connected with some cost. If any activity is completed after the deadline, some charge and some cost is attached with this. Okay, so that cost we want to minimize for the all activities actually. Okay, if any activity is completing after the deadline, so some cost is related. So in this case, what lateness term we are using here, so some lateness, LETNES, okay, lateness things. Okay, how much late our activity is completing after the deadline. So we are calculating this value for each activity. So we have to perform all the activity. Okay, and if we start these activities, suppose if I am just performing this activity in the current given order, so how we will perform this? So first activity, you can see that we are starting at 10 0, and it will complete at 3. Okay, so this activity ID 1 activity is completed before the deadline. So if any activity is completing before the deadlines, so that means this is not late, this is completing before the time. So we will consider this lateness time is 0 for this. Sorry. Okay, so this first job is completed. Yeah, sorry, 1 second. Sorry. Okay. So first activity is completed before the deadline, that means it is not late. We consider that lateness is 0 for this. Okay, second activity can be start after the completion of the first activity. Okay, because we are using the same one machine for this, like one like printer. So printer example is given, I think, for the lecture. So if you are using one printer, so suppose first job is completed at some time, then we can start the second job. So here
is equivalent to the best time, or we will have to maintain a separate record of the completion time?
That I am just trying to explain here. First, we are calculating the lateness things, okay, for the each. That it will clear, okay. So actually, we are just calculating the lateness of the each activity if we are performing in some sequence. So now this time we are performing in the given sequence. So first activity is completed at 10:03. So this is completed before the deadline. Okay, so deadline is also given. If any activity is completed before the deadline, so there is no lateness, so 0. Okay, then we can start the second activity. Suppose we start the second activity at time 3. Okay, so this is the end of first activity. Second we can start. So 3 plus 2, it takes 2 time. So 3 plus 2, it will complete at 5. Okay, So this is also completed before the deadline. Okay, so this is the second activity is completed at 5 and before the deadline, so lateness is 0. This is also not late. And next activity 3, so 3 we can complete at time 6. Okay, so 5 plus 1 is 6, so this third activity is also completed at before the deadline. Okay, so lateness is 0. Now next activity 4, if we start at time 6, 6 plus 4, 10. Okay, so that means it become 10 at the 4 activity, so it is ending on 10, but the deadline time is given 9, so it is late. Okay, how much time it is late? 1 time, so 10 minus 9 is 1, so here lateness is 1. Okay, now next activity is 5th and it takes 3 times, so 10 plus 3 is 13, so 13, this is the 5th activity, and what is the deadline for is 14, so it is completed before the time. Yeah, fine, so this is 0. And next activities take 2, so it will complete at the 15, so deadline is 15, so no lateness, 0. Okay, so this problem is given in that way, and if we are following this process and we are getting this lateness for each activity. So what our goal here is what is the maximum value in the all lateness. Okay, what is the maximum value in all lateness? Here is 1. Okay, suppose we are getting some different lateness value. Suppose we are getting like 0, 1, 3, 0, 2, 5, like this. Okay, so what is the maximum lateness of this all lateness? So this is 5 here. Okay, so here our goal is to minimize this maximum lateness value. This should be minimized. That means we want to minimize the lateness for all jobs, and here we want to minimize this lateness, this maximum value of all lateness. Okay, so this value should be minimum. So this is called as a minimized lateness. So first we will calculate the lateness of all, we will find out the maximum, then that value should be minimum in all possible order. So here we are getting 1 by chance. Okay, so we are following the same order and we are getting 1. I think this is the answer for this problem. But if we just change the order, okay, so suppose if we change some order for this, so this value will become changed. So I'm taking some different order this time. Suppose I'm taking this order like 4, 3, 2, 1, 5, 6. Okay, this order activity. So what lateness we will get? Okay, so we are starting from 0, so we are first perform this 4. Okay, so it will take 4 time. Okay, so at 4 it will complete this 4 activity, so this is now 0, so lateness we are getting it 0 here for 4. Now next we will select this 3, so 3 takes 1 time. Okay, so this will complete at 5. Okay, and this is 3. So still 1, or what is the lateness for 3 is 8. So still lateness value is 0. Now next one is the 2. So 2 will take 2 times. So 5 plus 2, 7. So it will complete at 7. This is the activity ID 2. So deadline is 9. Before deadline, so it is also 0. But when we are taking 1, so 1 is completing now, taking 3. So 7 plus 3 is 10. Okay, and deadline is 6, so 10 minus 6 lateness is 4. Okay, and next activity we are taking 5, so 10 plus 5 is 15, so 15 it is completing at 15. So this is 1 and this is 5. Now deadline is 4, so we are getting 1 lateness here, and 15 plus 2 last 6. Okay, so this is 17. And this is a 6, so deadline is 15, so this is also difference 2. Now you can see that we are getting this lateness. If we are changing the order, we are getting different lateness value. So here what is the maximum lateness among all? 4. Okay, this is the different one. So our goal is here to minimize this maximum lateness among all, this value. So how we can solve this? So first thing, many of you are confused. Some maybe you will add all the lateness and you want to try to minimize that. So that is not the correct. Here we want to minimize the maximum lateness among all. Okay, so here we are getting 1 in this case. So how we can use any straightforward algorithm to solve this? Here we are just taking to random order. Okay, first it is given as the input, and second order we have just taken randomly. So how we can solve this problem in the specific way, is in the standard way. So the algorithm is
So the second column is what have you written?
second column is the worst time. That means how much time job is taking. So in terms of the, if suppose if we are taking the printer problem, okay, suppose we have some request to take the print out and in the bulk documents. So we have many requests for the printing, and this printing operation takes some time. Okay, so suppose if we are performing first printing operation, or we are taking some printing, it will take some time. Then after completion of this first job, then we can start the second. So how much time the job is taking, that time is given this as a worst time. Okay, and
Okay.
what deadline is given, that means what is the maximum time is the
Before which you have to
given.
complete.
Yeah, if we are completing before that, it is okay, there is no lateness, we are not late. If we are doing after the deadline, that means we have some cost.
So the lateness is the deviation from the deadline.
Yes. Yeah. So that maximize what is the maximized lateness among all the lateness, that value we want to reduce to minimum. Okay.
Okay.
So this is the minimized lateness problem. So here how we can solve this? So what is the standard way to solve it? So sort all the job in ascending order of the deadline. So this is the similar to the previous one. At the time we are sorting all the jobs of the end time. Here we will sort the jobs in the increasing order based on the deadline, what deadline is given. After that, we will just perform the similar things. Start with time t0 for each job in the so this is the first step. After that, perform the same things which I have just performed. Okay, so for this previous problem, so we are getting this one answer by the random order. But if we solve by the process of this, so first we have to sort this activity by the deadline. So first this 6, then 8, then 9, 9, 14, 15. Okay, so that means order should be like this. So 1, and then 3, then 2, then 4, then 5, then 6. Okay, so our job order should be like this based on the deadline. Okay, so 1, 2, 1, 3, and 2, 4, 5, 6. If we follow this order, so what is the start time for this one is same things we can do this. So we will start from the 0, and if we are performing 1, so it will complete in 3 times. So 3 times it will take. So it will complete at 3. So this is completed before the deadline. So lateness value is 0 for 1. Okay, next activity we will perform for 3. So 3 is taking 1 time. So that means it will complete at 4. Okay, so it is also completing before the deadline, 0. And next is the 2. So 4 plus 2 is 6, will complete at 6. And okay, so before the 9, 0 lateness. And next activity is 2. Sorry, 2 is already done. And 4. So 4 is taking 4. So 6 plus 4 is 10. So here this is 10. Okay, now deadline is 1 for this. Okay, after 9. After that, next activity is taking 3. So 10 plus 3 is 13. And before 14, so 0. And next is 13 plus 2, 15. So on time. Okay, so this is also taking. So you are getting this lateness, and here what is the maximum value? 1. And this is the actually minimize. You cannot get the optimal answer compared to this one. Okay, so this is the minimized lateness 1.
Here we have sorted based on the deadline.
Yeah, here we are sorting based on the deadline.
Yeah.
Okay, so you will always get the minimized maximum lateness among all the lateness. Okay, so this is the next greedy algorithm.
Sir,
Hmm?
sir, when we are getting four,
Hmm. So here, if we are following this order, like, so we are selecting 4 first, 4 ID first, 3, 2, 1, 5, 6. At that time, you can see that we are getting this lateness 4, 1, 2, 0, 0, 0. So what is the maximum value among all 4? Okay, so this is the not optimal solution. This order is not the correct providing the optimal solution. But if we are following this deadline after sorting the deadline, okay, then we are getting this maximum value 1 among all. Okay, so this is the optimal answer for this.
sir, we are not sorting the deadline. We are sorting the time that.
No, deadline. So this you can see that this is the deadline value. Based on that, I have sorted this sequence. So this sequence. Okay, so first is deadline is 6. Okay, third one is the 8. Okay, 2 is the 9, then 14, 15. Can you see this? Sir?
So how it is matching with this time?
Where is the
Just
timing is just we have to calculate. We will always start from the 0 value. Okay, now we will simply take in this order. We will take job in this order. We will select first job and we'll take what is the time required for the first job. So we will add the previous value 0 plus 3. So this is the last time is 3. Okay, for first activity. When we are selecting next job, this ID is 3. So ID is 3. So it is taking 1 time. So we will add this 1 into previous one. So 3 plus 1, 4. Okay, and so what is the deadline for this is 8, and we are completing this at 4, so it is completing before the deadline, so it is latest value is 0. Okay, so the ID 1, then 3. After that we will check the next, which one is the next one, 2. Okay, so what is the time required for 2 is 2. So 4 plus 2 we will add in the previous end time. So 4 plus 2, 6. So that means we have completed this 2 at time 6. And what deadline is given? 9. Before that, okay, so this is also 0. And next one is in the given order 4. Okay, so 4 IDs takes 4 time. So 6 plus 4, 10. So this is for 4 ID, 10. And what is the deadline for given is 9. So it is completing after 1 of the deadline. So because of that, lateness is given here 1. Okay, now we are selecting 5. Okay, so 5, what is the time required for 5 is 3. So 10 plus 3, 13. So it is completing at 13 and deadline is given 14 before deadline. Okay, so it is taking lateness is 0. Okay, then we are selecting this 6 and 6 taking 2 times, 13 plus 2, 15. Okay, and deadline is also 15. Okay, so 15, so lateness is 0. Okay, so in that manner we are calculating this, and what time our activity is completing. It is completing before the deadline, then lateness is 0, or if it is completing after the deadline, then we will calculate the lateness. Okay, and then what is the maximum value among all the lateness, all the jobs lateness is 1. So this is the optimal solution. You cannot achieve more optimal answer compared to this. Okay, so after first we are performing the sorting based on the deadline, then we are selecting the jobs in the given order. Okay,
so this 1, 3, 2, 4, 5, 6.
this is the job ID. This is based on the sorting. So if you sort this ID, if you sort this jobs based on the deadline, so which will come first? What is the smallest deadline?
6.
Is 6. ID is
1.
Okay,
got it. Yeah,
and this is next one is the 8.
yeah.
Okay, ID
So
is 3. Next one is the 9. You can also take this 2. So if you are getting 9 and 9 here, so you can take any order. So 2 and 4. So we are taking 2. Okay, for next 9, this is 4. Next 14 and then 15. So 5, 6. We are written ID here. Okay, but when we are calculating the time, we are consider this. We are considering this. And when we are calculating the lateness, we are comparing with deadline.
Got it.
Okay. So this is one problem, and last problem is the Huffman algorithm. This is also one greedy algorithm based problem. So Huffman algorithm is basically used for the compression techniques, where we want to reduce the code size. So if you know that this topic is actually related to some computer network things. So every data which we send on the network, actually first we compress the data, encrypt the data, then we will send to the network. Okay, we cannot directly send the actual data in the same form in the networks because anyone can hack. So some operation performed before that. So we perform the compression operation, we perform the encryption option, we will just change the one form into the another form, so nobody can understand in between on the network to hack. Okay, so this operation is performed in the networking. So there is one operation is performed compression operation. Okay, so it's just data compression. So how we can perform this data compression, how we can generate the code for the symbol. So this is the Huffman algorithms. So where it provides some codes for the characters based on the frequency. Suppose I'm taking some example here for this problem. We have some message to send on the network. Okay, where we have some character A, B, C, D, E. Okay, and our message is created only these 5 characters. Okay, we are only using these 5 characters in our message. Now the frequency of each character may be different. Okay, suppose I'm just taking some examples. So here this is repeating. So we have total 100 character. We have total 100 character using this A, B, C, D, E, where the A is repeated 30 times, B is repeated 5 times, C is repeated 20 times, D is repeated like 50 times, so not 50, 40 times, and E is repeated 5 times. I think that it is sum up is 100, 30, 50, yeah, 50. Okay. So the frequency of each character is looking like this. Okay, so A is 30 times repeating in 100 character, B is repeating 5 times, C is repeating 20, D is repeating 40, and E is repeating 5 times. And we are getting total 100. Now we cannot send this message in the same actual form A, B, C, D, E. So we will convert into a binary form. Okay, so 0101 form. So we need some equivalent code for A, B, C, D, E. Okay, in the binary form. Suppose if we are following some specific length code for this A, B, C, D, E, and our length for the code is like 4-bit for each. Okay, so what we will do, so if every character have 4-bit length, so how many total bits are required to send this? 100 into 4. Okay, 400. Suppose this frequency may be in higher order, like 10 to the power 3. So total bits is required 4 into 10 to the power 3, like this. Okay, so if we are using fixed length code for the each character, so our bits is actually taking this number of size. What another techniques we can use to compress this? So we can generate the codes for each character based on the frequency. So which character which have the highest frequency, we generate the small length code for that. Which character is taking a smaller number of frequency, we can take the bigger length of the code. Okay, so instead of taking fixed length code for the each character, we can develop the code, small code for the highest frequency and biggest length code for the lowest frequency. In that way, we can achieve some compression in the number of bits. Suppose this A is taking like 2 bits, okay, and this D is taking like 1 bits, and this is taking like 3 bits, and remaining is taking 4 bits. like, okay. If we generate the codes in some by some algorithm, and that code should not be similar, okay, and that code can we easily identify which character is represented by the code. So if we generate the code in this manner, so how we can achieve some efficiency in the terms of size? So here what we will do, so what is the total bits is required now for the 100 character? Okay, so 30 into 2 60, 5 into 4 20, 20 into 3 60, okay, 40 into 1 40, 5 into 4 20. If you add all these, so you can see that 0 and 8 14 18 20, 20 200. Okay, so here you are getting initial previous example, we are taking 4 length code for the each character, we are getting 400 bits. Here we are getting 200 bits. Okay, so the Huffman algorithm is actually provides the Huffman codes for this type of problems, this type of compression techniques. So some frequency is given for some characters, then we can generate the code using the Huffman algorithm. Okay, so how we can, what is the algorithm of this Huffman? Now we will just check what is the process, and this is a greedy approach. So this is just an example to reduce the code. So in this case, you can see that if we just calculate the frequency for 10 to the power 3 characters, so we will get that 2 into 10 to the power 3. So 50% we are reducing the bits. So you can see that we are achieving some compression. So Huffman algorithm is generating the codes in this manner. So how the Huffman algorithm works? So we have given this frequency for each character as a problem. So A, B, C, D, E. So 30, 5, 20, 40, and 5. Okay. So this is given as a problem. So we have some characters, we have some frequency, and how we can generate the codes for each character. Okay. So now how the algorithm works. So algorithm always select two smaller weights or smaller frequency first, and it creates a Huffman tree from bottom to upside, bottom to top manner. Okay, so what we will do, we will just select the two smaller frequency first. Okay, and when we will create the Huffman tree from the bottom upside. So we are selecting like this. This is the frequency 5, and this is the frequency 5. So in this Huffman tree, always leaf node will always represent the actual frequency of the character. So we can just mention this like this is for B and this is for E. Okay, after that we will just add both value 5 plus 5 10. Okay, so this is the internal node. When we are creating the tree in the bottom up manner, so the leaf node will always represent the actual frequency of the character, but internal node just the sum of the frequency. So this is the first process. This process we will repeat again and again until we will complete all the nodes. So 5 and 5 we select at the first time. After that we are getting this frequency. So 30 is not used yet. So 5 and 5 now we are getting so 20 is not used and 40 is not used. Apart from that, one node we are getting by sum this. So 5 plus 5 10. Okay, so this is internal node. I am just marking this as a round. This is not a frequency of any character. This is just an internal node which we are getting after sum. Same. So this is the first step. Same things we will perform again. Again, select two smaller frequency in the remaining one. So what are the two smaller one is 10 and 20. Correct? Out of this 30, 20, 40, and 10. So 20 and 10 are the two smaller frequency or two smaller weights. So 10 is already available in the tree. 20 is the frequency of C. This is the exact frequency. Okay, so we will create new node with this 10. Okay, like this. You can create on the left or right any side. Okay, and 20 you will just store, and this is the leaf node, and this is representing the C frequency. Okay, and just add up 10 plus 20 30. Okay, this is the internal node. Now third step, once again same thing. So 30 is not used, this 20 and 10 we have used, so 40 is the actual frequency. Now we will just represent this 10 plus 20, 30 node, okay, in some place. So 30, this is the internal node. Now once again same process we will repeat again. So 30, 30, you can see that next to smaller value. So always we are selecting two smaller values. So this is the greedy steps. Okay. So because of that, this is a greedy algorithm. So 30 and 30. So that means 130 is the frequency of A and 130 is the internal node value. So we will once again create a new node as a leaf node. So this 30 and this is representing A. And after that, we will get this as a 60. Now next step, we have 140 value remaining and we have some 60 value as internal node. Okay. Now we have only two value remaining, so these are the two smaller. Okay. So once again, this is the frequency, so 40. Okay. And we will add this 100. So after that, we will get the total frequency of the each. Okay. And this 40 is representing D. So this is the process to create Huffman tree. So this is called as a Huffman tree. After that, how we can generate the Huffman code for each. So the process to generate the Huffman code is A, B, C, D, E. Okay. Just mention 0 on the left edge, 1 on the right edge in the tree. Okay. Every left edge just mark 0. And every right edge just mark the 1. Okay. To generate the code, traverse from the root to leaf. Okay. So what is the code for A? So just traverse from root to leaf. So what edge value is coming in the sequence? Okay. So from root 100, so this 100 to A 30. Okay. So 0 and 1 coming in the path. So 0 and 1 is the code for A. And what is the code for B? So you can see that from 100, 0, 0, 0, 0. So code for B is 0, 0, 0, 0. And what is the code for C? So 0, 0, 1. 0, 0, 1. What is the code for D? Only 1. Okay. What is the code for E? 0, 0, 0 and 1. 1. So now we get the code. This code is actually called the Huffman codes. And what is the length of each code is 2. This is 4. This is 3. This is 1. This is 4. This is the length, okay, of the each code. So we can generate the code in that manner. First step is to create the Huffman tree. Second step, just mark 0 and 1, 0 on the left and 1 on the right. And after that, just traverse from root to the leaf node to find out the code and what is the length of the code. So here 2 bits, 4 bits like this. Okay. And we are getting this Huffman. So this Huffman code may be changed. Suppose if at the selection time, so we can, when we are selecting this 5 and 5 first, so maybe we can just take this B on the right and E on the left. So some code may be changed, but the length will remain same. Okay. So here, this is the Huffman codes. This process length we are getting. So this is the length of the code. And what is the property? So this is the concept of Huffman algorithms. How we will generate the Huffman tree and Huffman codes. And there is one property in the Huffman codes that is generally called these codes are prefix code. We are saying this is code. These Huffman codes is always generate. Huffman algorithm is always generate the prefix code. So what is the meaning of this? So meaning of this is any code of any character cannot become as a prefix of another code. So if you see the property of this, if you see any code cannot become as a prefix of another code. So suppose this D. Okay, so code is generated only one. So this one cannot become as a prefix of another code. So one is not coming as in the prefix part. Similar, if you're considering this 0, 1. 0, 1 completed is not coming as a prefix in any other code. Okay, so any code cannot become as a prefix code. So this is the property is generated by the Huffman codes. So this is the property. So this type of question is also asked in the exam. So some codes are given like this. So A, B, C, D, E, and some random code is given in the question. So like 0, 1, 1, 1, 0, like 0, 1, 0, and 0, 0, 1 and 1 1 1 like this. So this type of question asks that this is the valid code or not by some Huffman codes, valid Huffman codes or not. So how you can identify this is the valid Huffman codes or not? So you can check this prefix property. So you can check this 0 1. 0 1 is coming as a prefix of in the another code. Okay, so here you can see that 0 1 is also coming in the as a prefix of C. Okay, so this is not possible in the Huffman code. So you can just revert the answer. This is invalid code, invalid Huffman codes. So check this property in the Huffman codes, and you can just return the answer. It's not the correct code. Okay, so this is one property which is important for the Huffman. So
D and E are prefix codes.
D and E.
B for Bombay and E for elephant.
This is okay because this complete code is not coming as a prefix. We always look the complete code, not the part of.
Okay.
Okay. So this is okay. 110 and 111 both have the same length and both have the difference. So we can not consider this. Okay, but here this 01 complete code is coming as a prefix in the another code. So in the we can also understand these things in the tree manner. So that means if 01 this 01 is coming for A and 0 1 0 is coming in the another code. That means we always traverse from root to leaf, but this is not representing the leaf because 0 1 that means we are coming from the root, so we are coming like from the root 0 and then 1. Okay, still there is 1 0, so that means 1 0 is also remaining like this. Sorry, this is not the correct. So for 0 is left and 1 is right. Okay, then still left. Okay, so 0 1 0 like this. We are coming in this path manner. Okay, but 0 1 is coming, that means we are coming from the root on the same path and we have stopped at this. So this node cannot be represent the leaf node because still there is one path is remaining which is mentioning by this C. So Huffman code is only represented the path, complete path from root to leaf. Okay, so this 0 1 is not possible. Okay, because here one node is there, that means path is also contains some more length. So this is the Huffman code algorithm, Huffman algorithm. Okay, so how we can generate the Huffman tree first? So you should know how, if frequency are given, then how you can create the Huffman tree. So always select first two node and create the Huffman tree in the bottom up manner. And after generating the tree, just create the Huffman codes by traverse. Just first mark the 0 and 1 on the left or right edge. Then just traverse from root to leaf node for each character code. Okay, and then you can return the length of each code. So yeah, this is the topics of the week 7. Any query in this?
It's already 3 hours, sir. So it's totally mentally tired.
Okay. So I hope the topics concepts are clear. Just try to just take some example and try to solve all these topics by yourself. Okay, to understand better. Okay.
Sir, for the code of which topic is important in this week?
Sorry, which topic is important in this week? You're asking?
Code.
Code.
Yeah.
Okay. So I'll say implementation part is important, not only for the exam purpose, but for the future purpose, all the important. But yeah, in this week, that interval scheduling, yeah, that interval scheduling types of implementation you should know. AVL definitely we generally not ask on the OPP exam or any code related questions of the AVL tree. But this interval scheduling, Huffman, conceptual part should be clear. Cool. So this week we generally ask the conceptual question in the quiz. Okay, interval scheduling is important maybe for OPP. So some problems may be created based on the interval scheduling, and that you can solve. Okay. Any question, any query? Okay, so if there is no query, then I think we can wind up the session. Thank you everyone.
Thank you, sir. Thank you very much.
Okay, good night.
Yes, sir.
Good night.
Bye.